200 billion stars in our galaxy, 2 trillion galaxies in the observable universe. More stars in the cosmos than grains of sand on every beach on Earth. And when we point our most sensitive instruments toward all that vastness, when we scan the skies for signals, for transmissions, for any whisper of intelligence beyond our own, we hear nothing. Not silence in the poetic sense. Silence in the most literal, most unsettling way possible. No radio bursts, no megastructures blocking distant starlight, no probes visiting our solar system, no ancient messages encoded in cosmic radiation, just an empty channel stretching across 200 sextillion stars, as if we are screaming into a room where every seat is occupied and no one will answer back. This is the Fermi Paradox. A question so simple, a physicist asked it over lunch in 1950, and so profound that 70 years later we still cannot resolve it. Where is everybody? The math says they should be everywhere, billions of planets older than Earth, billions of years for life to evolve, spread, build. The universe has had more than enough time to fill itself with civilizations, and yet we appear to be alone. The explanations science has proposed are not comforting. Some suggest we have already survived a cosmic filter that kills nearly everything before it reaches our level. Others suggest the filter is still ahead, waiting in our future like an evolutionary wall we cannot see. A few argue that advanced life is out there, but hiding, staying silent, afraid of what might hear them if they speak. This video walks through 30 of those answers, 30 attempts to explain why a universe built for life has given us only quiet. Some will challenge what you assume about intelligence, others will reframe what survival actually means at cosmic scale, and a few will make you wonder whether being alone is the best possible outcome. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. 200 billion stars. That's the current estimate for how many suns are burning inside the Milky Way galaxy right now. Not 100 billion, not 300 billion, 200 billion, and that's just one galaxy, the one we happen to live in, the one whose light we see arching across the summer sky like a river of fire when we're lucky enough to be standing somewhere dark enough to notice. 200 billion is not a number the human brain was built to comprehend. You can say it, you can write it down, you can even do math with it if you're patient. But you cannot picture it. Not really. If you tried to count to 200 billion out loud, one number per second, never stopping to eat or sleep or breathe, it would take you more than 6,000 years. Entire civilizations would rise and fall while you were still counting stars in a single neighborhood of space. Carl Sagan used to say there are more stars in the universe than grains of sand on all the beaches of Earth. He wasn't being poetic, he was being precise. And even that comparison undersells it, because the Milky Way, for all its scale, is one galaxy among trillions. For most of the 20th century, astronomers estimated there were roughly 100 to 200 billion galaxies in the observable universe. That was the number you'd find in textbooks, the one repeated in documentaries, the one that already felt incomprehensibly large. Then in 2016, a team led by Christopher Consolis published a study in the Astrophysical Journal that revised the count upward by a factor of 10, 2 trillion galaxies, not 200 billion, 2 trillion. They didn't find new galaxies by accident. They used deep field imaging from the Hubble Space Telescope and ran models of how galaxies evolve and merge over cosmic time. What they discovered was that the early universe was far more crowded with small, faint galaxies than anyone had realized. Most of them have since merged into larger structures, but they were there, and when you add them all up, the total number of galaxies that have ever existed in the observable universe jumps to something closer to 2 trillion. Census himself said it plainly. We found 10 times more galaxies than previously observed, suggesting a universe far more crowded with potential life. Crowded is an understatement. If you take 2 trillion galaxies and assume each one contains on average 100 billion stars, you get 200 sextillion stars. That's a 2 followed by 23 zeros, 2 times 10 to the 23rd power, if you want to write it the way physicists do. Some estimates push the number even higher, closer to 300 sextillion, depending on how generous you are with the galaxy counts and the average star populations. Either way, the number is so large it stops meaning anything. It becomes a wall of zeros your mind slides off. But here's the thing. Those stars are not decorations. They are not background noise. Every single one of them is a sun, and most of them have planets. For decades, astronomers assumed planets were rare. Our solar system was thought to be a lucky arrangement, possibly one of only a handful in the galaxy. Then, in the 1990s, we started finding exoplanets. At first, it was a trickle. One planet here, another there, all of them massive gas giants orbiting close to their stars in configurations that made no sense according to the models we'd built from studying our own neighborhood. Then the Kepler Space Telescope launched in 2009, and the trickle became a flood. Kepler stared at a single patch of sky containing roughly 150,000 stars and watched for 4 years. It found thousands of planets, not dozens, thousands. And when scientists extrapolated from that sample, the conclusion was unavoidable. Planets are everywhere. Current estimates suggest that 20 to 50% of stars host rocky planets in what's called the habitable zone. That's the region around a star where temperatures allow liquid water to exist on a planet's surface. Not too hot, not too cold. The Goldilocks zone. 20% is a conservative estimate. Let's use it anyway. 20% of 200 sextillion stars is 40 sextillion planets, where liquid water could theoretically pool on the surface. 40 sextillion places where, if conditions are even remotely similar to early Earth, chemistry could start doing interesting things. Amino acids could link into chains. Chains could fold into proteins. Proteins could begin catalyzing reactions that weren't happening before. Metabolism, replication, evolution, life. The Goldilocks principle used to feel like a narrow constraint. A planet had to be just the right distance from just the right kind of star, with just the right atmosphere and just the right amount of water delivered at just the right time. It sounded like a lottery with impossible odds. Except the universe has been running that lottery for 13.8 billion years, and it's bought trillions of tickets in every drawing. When the sample size is that large, even vanishingly rare events stop being rare. Let's talk about Earth for a second, because Earth is the only data point we have. The planet formed roughly 4.5 billion years ago from the debris disk around a young sun. For the first few 100 million years, it was a molten hellscape, bombarded by asteroids and comets, too hot for liquid water, too chaotic for anything resembling stability. Then it cooled, oceans formed, and within a few 100 million years, maybe less, life appeared. The earliest evidence for life on Earth dates back somewhere between 3.5 and 4.1 billion years. That means life didn't wait around. It didn't take billions of years of failed experiments and lucky breaks. It showed up almost as soon as the conditions allowed. Abiogenesis, the process by which non-living chemistry becomes living biology, happened fast, suspiciously fast. Which suggests one of two things. Either Earth got extraordinarily lucky in a way that almost never happens anywhere else, or abiogenesis, given the right conditions, is not that hard. If it's the second option, and the evidence increasingly points that way, then life is not rare, life is common, maybe even inevitable. You give a planet liquid water, a source of energy, and a few 100 million years, and chemistry starts organizing itself into something that eats, grows, and reproduces. That's what happened here, and here is not special. Our sun is a middle-aged yellow dwarf, one of the most common types of stars in the galaxy. Our planet is a rocky world in the habitable zone, a configuration now known to be abundant. The raw materials for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, are some of the most common elements in the universe. There is no exotic ingredient in Earth's recipe, no unobtainium, no rare isotope delivered by a 1 in a trillion event. Everything that made life here is sitting on countless other worlds right now. So where is everybody? Before we get to that question, and it is the question this entire video is built around, we need to talk about the Drake equation. In 1961, a radio astronomer named Frank Drake organized the first scientific meeting on the search for extraterrestrial intelligence. It was held at the Green Bank Observatory in West Virginia, and it brought together a small group of scientists who were willing to take seriously the idea that we might not be alone. To frame the discussion, Drake wrote down an equation, not because he thought it would give a precise answer, but because it was a way of organizing the problem, a way of breaking down a single, overwhelming question into smaller, more manageable pieces. The equation looks like this, and I'm going to walk through it in plain language because the symbols don't matter as much as what they represent. You start with the rate at which new stars form in the galaxy. Then you multiply by the fraction of those stars that have planets. Then the average number of planets per star that could support life. Then the fraction of those planets where life actually appears. Then the fraction where life evolves intelligence. Then the fraction where intelligent life develops technology capable of communication. And finally, you multiply by the length of time such a civilization remains detectable. The result, in theory, is the number of communicating civilizations in the Milky Way right now. Drake himself said it best. The equation is a way of organizing our ignorance about the existence of other life. And he was right. Because even though we've learned an enormous amount since 1961, most of the terms in that equation are still educated guesses at best. We know the star formation rate pretty well. We know the fraction of stars with planets pretty well. We're starting to get a handle on how many of those planets sit in habitable zones, but everything after that is speculation. We have no idea what fraction of habitable planets develop life. We have no idea what fraction of life-bearing planets develop intelligence, and we have no idea how long technological civilizations last. We have exactly one example. Us. And we've only been capable of interstellar communication for about a century. A blink, a rounding error in cosmic time. Here's what makes the equation uncomfortable. Even if you plug in extremely conservative numbers, numbers that assume life is rare and intelligence is rarer, you still end up with thousands of civilizations in the Milky Way alone. If you use optimistic numbers, the kind that assume life emerges wherever conditions allow and intelligence follows naturally given enough time, you get millions, and that's just one galaxy. Scale it up to 2 trillion galaxies, and the number of civilizations in the observable universe becomes so large it stops being a number and starts being a certainty, a statistical inevitability. Life should be everywhere. Intelligence should be common. The galaxy should be humming with signals. We should be tripping over evidence of other civilizations every time we point a telescope at the sky. Let's zoom out for a second and talk about time. Because time is the other piece of this puzzle that makes the silence so strange. The universe is 13.8 billion years old. Our sun is 4.6 billion years old. That means the universe existed for more than 9 billion years before our solar system even formed. Stars were being born, planets were coalescing, chemistry was doing its thing for 9 billion years before Earth showed up. The peak of star formation in the universe happened roughly 11 billion years ago. That was the era when galaxies were churning out new stars at the highest rate in cosmic history, which means the majority of stars in the universe are older than ours, and the planets around those stars are older too. If life emerged on any of them at roughly the same pace it emerged on Earth, those civilizations have had a billions of years head start. Not millions, billions. Think about what humans have accomplished in the last 10,000 years. We went from hunter-gatherers to agrarian societies to industrial civilizations to spacefaring species in the blink of an eye by geological standards. 10,000 years is nothing, it's a sneeze. Now imagine a civilization that had a billion-year head start. Not 10,000 years, a billion. What would they look like? What would they be capable of? Would they still be biological? Or would they have merged with their technology centuries ago? Would they still be confined to planets, or would they have dismantled their home star to build megastructures we can barely imagine? Would they still communicate with radio waves, or would they have moved on to something we don't even have a name for yet? The universe has had more than enough time to fill itself with ancient civilizations. The raw materials are abundant, the opportunities are endless. The timeline stretches back billions of years before we arrived. And yet, when we look out into the cosmos, when we point our most sensitive instruments at the sky and listen, we hear nothing. No signals, no patterns, no evidence of engineering at the scale you'd expect from a species with a billion-year head start. Just the faint hiss of hydrogen clouds and the background radiation left over from the Big Bang. The galaxy is not humming, it's silent. And that silence, given everything we know about the scale and age and chemical richness of the universe, is one of the most unsettling facts in all of science. Earth is not special. Our sun is not special. Our location in the galaxy is not special. The elements that built us are common. The timeline that allowed us to exist has played out countless times before. Every statistical model we have says we should be surrounded by neighbors, and yet we appear to be alone. Not just rare, not just isolated by distance, alone in a way that makes no sense given the numbers. If you do the math honestly, if you take the 200 billion stars in our galaxy and multiply by the fraction with planets and the fraction of those in habitable zones, and give even the most conservative estimate for how often life emerges, you end up staring at a universe that should be teeming with life, a universe where we are not the first, not the most advanced, not even particularly interesting. Just one more voice in a crowded conversation that's been going on for eons. Except there is no conversation, there are no voices. There's just us, standing on a small rocky planet orbiting an average star in the outer arm of an unremarkable galaxy, shouting into the void and hearing nothing shout back. That's the setup, that's the cosmic census. 200 billion stars in the Milky Way. 2 trillion galaxies in the observable universe. Planets everywhere, habitable zones common, life emerging fast wherever conditions allow. Billions of years for civilizations to rise, expand, and leave marks on the cosmos that should be visible from here. And yet the universe is silent, completely, utterly, maddeningly silent. So what happened? Where is everyone? And more importantly, why aren't we hearing from them? Those are the questions that keep astronomers awake at night. And the answers, when you start listing them out, range from uncomfortable to terrifying. The question was asked over lunch. That matters because the most profound mysteries in science have a habit of sneaking up on people during ordinary moments. A sandwich, a coffee, a paper napkin with someone's handwriting scrawled across it. No dramatic music, no eureka moment staged for posterity. Just a physicist sitting in a cafeteria thinking out loud and accidentally putting his finger on one of the strangest problems in modern cosmology. The physicist was Enrico Fermi. The year was 1950. The location was Los Alamos National Laboratory in New Mexico, a place still humming with the aftershocks of the Manhattan Project. Fermi was eating lunch with three colleagues, Edward Teller, Emil Konopinski, and Herbert York. The four of them were talking about something completely unrelated, a recent spate of reported UFO sightings that had been making the rounds in newspapers. The conversation was light-hearted. No one at the table believed flying saucers were visiting Earth. They were physicists. They dealt in evidence, not tabloid speculation, but the topic got them talking about interstellar travel, the speeds required, the distances involved, the question of whether any civilization could realistically cross the gulf between stars. And then Fermi, in the middle of the conversation, asked a question that wasn't really a question. It was more like an observation wrapped in 4 words. Where is everybody? The table went quiet. Not because the question was profound in the moment, because it was obvious. If the galaxy is as old as we know it to be, and if intelligent life is even remotely common, then someone should have gotten here by now. Not us going to them coming to us. Millions of years ago, billions even. The galaxy has been around for more than 13 billion years. Our solar system is only 4.5 billion years old. That leaves an 8.5 billion year head start for anyone who happened to evolve earlier. If even one civilization in all that time had developed interstellar travel and decided to expand outward, their descendants or their machines should have colonized every habitable star system in the galaxy by now, including ours. Fermi wasn't talking about flying saucers. He was talking about the absence of flying saucers, the absence of radio signals, the absence of megastructures, the absence of any evidence whatsoever that anyone else had ever been here or was out there right now doing anything detectable. Given the size of the galaxy and the amount of time available, Earth should have been visited, colonized, or at least observed by now. And it hadn't been. That was the puzzle. Not where are they hiding, where are they at all? The paradox didn't get a formal name until much later. It wasn't published in a paper. Fermi didn't write it down as a theorem. It just sat there in the background of cosmology like a stain no one wanted to talk about. For years, most scientists assumed the answer was simple. Space is big, interstellar travel is hard. Maybe life is rarer than we think. Maybe intelligence almost never happens. Maybe civilizations destroy themselves before they get the chance to spread. Pick your explanation and move on. The paradox only became impossible to ignore once we started doing the math seriously. In 1961, a radio astronomer named Frank Drake organized a meeting at the Green Bank Observatory in West Virginia. It was the first serious scientific conference on the search for extraterrestrial intelligence, and Drake wanted a way to frame the discussion. So he wrote down an equation, the Drake equation. It was never meant to produce an exact number. It was a way of structuring the problem, a checklist of variables you'd need to estimate if you wanted to guess how many communicating civilizations might exist in the Milky Way at any given time. Start with the rate at which stars form in the galaxy. Multiply by the fraction of those stars that have planets. Multiply by the number of planets per star that could support life. Multiply by the fraction where life actually emerges. Multiply by the fraction where life evolves intelligence. Multiply by the fraction where intelligence develops technology capable of communication. And finally, multiply by the average length of time such a civilization broadcasts detectable signals into space. The result, in theory, is the number of civilizations we should be able to detect right now. Drake's original estimate, using the numbers that seemed reasonable in 1961, came out to about 10,000 civilizations in the Milky Way. 10,000. That wasn't a fringe guess, that was the moderate estimate. If you used optimistic numbers, the kind that assumed life was common and intelligence followed naturally, you could get answers in the millions. Even the most pessimistic estimates, the ones that assumed nearly every step was a rare fluke, still gave you dozens, maybe hundreds, and we'd heard from exactly zero. That's when the paradox stopped being a lunchtime curiosity and started being a crisis. Because the Drake equation wasn't some wild speculation. It was built on reasonable assumptions using the best data available at the time. And every version of it, conservative or generous, pointed to the same conclusion. We should not be alone. The galaxy should be crowded, and the fact that it appeared to be empty was not a minor inconvenience. It was a direct contradiction of what the math said should be true. The response from the scientific community was to start looking harder. If the signals were out there, we just needed better instruments to find them. In 1971, NASA launched Project Cyclops, an ambitious proposal to build an array of radio telescopes specifically designed to scan the sky for artificial transmissions. The project never got full funding, but it set the template for everything that followed. SETI, the search for extraterrestrial intelligence, became a real scientific discipline with real money and real researchers dedicating their careers to listening. The idea was simple. If intelligent civilizations exist, they're probably using radio waves to communicate, just like we are. Radio is a natural choice for interstellar messaging. It's fast, it's efficient, and it travels through the vacuum of space without much interference. If someone out there is broadcasting, we should be able to pick it up. All we had to do was point our antennas in the right direction and wait. The most famous moment in SETI history happened on August 15, 1977. An astronomer named Jerry Eman was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope had been running a long-term survey sweeping across different regions of the sky, recording whatever signals came through. Most of the time the data was noise, background radiation, random static, nothing interesting, and then Eman saw something that didn't belong, a signal. Strong, narrow band, exactly the kind of transmission you'd expect from an artificial source. It lasted 72 seconds, then it vanished. Eman was so startled that he circled the printout in red pen and wrote a single word in the margin. Wow. The wow signal, as it came to be known, is still one of the most tantalizing pieces of data in the history of SETI. It came from the direction of the constellation Sagittarius. It was detected at a frequency of 1420 MHz, right in the middle of a protected band that's supposed to be reserved for radio astronomy because it's naturally quiet. No human transmitter should have been broadcasting there. The signal's intensity was 30 times stronger than the background noise. It matched every characteristic of what an extraterrestrial transmission might look like, and it never repeated. The Big Ear telescope scanned that same patch of sky more than 50 times in the years that followed. Nothing. Other observatories pointed their dishes at the same coordinates. Still nothing. The signal appeared once and disappeared, leaving behind a printout and a question mark that has haunted SETI ever since. In 2017, astronomer Antonio Paris proposed an explanation. A comet, specifically two comets, 266 P. Christensen and P. 2008 Y2, which happened to be passing through that region of space in 1977. Comets emit hydrogen, and hydrogen radiates at 1420 MHz. The signal, Paris argued, was natural, not aliens, just a comet that happened to be in the right place at the right time to look like something it wasn't. Some researchers accepted the explanation, others weren't convinced. The WOW signal's frequency was too precise, its strength was too high, and the timing, exactly 72 seconds, matched the length of time the telescope's beam would have swept across a stationary point source. If it was a comet, it was a suspiciously well-behaved one. The debate is still unresolved. But here's what matters. The WOW signal is the closest thing SETI has ever found to a genuine candidate for extraterrestrial contact. One signal, one time. In more than 50 years of searching. That's the scoreboard. Thousands of hours of observation, hundreds of thousands of star systems scanned, decades of effort by some of the brightest minds in astronomy, and the result is one ambiguous blip that might have been a comet. Fermi's question is still hanging in the air. Where is everybody? You could argue that we're not looking hard enough, and you'd be right. The searches we've done so far are absurdly limited compared to the size of the task. SETI has surveyed maybe a few thousand star systems in any real detail. The Milky Way contains 200 billion stars. That's like dipping a teaspoon into the Pacific Ocean, coming up empty, and concluding there are no fish. We've barely started. Most SETI efforts focus on radio waves, which makes sense given our own technology, but assumes that other civilizations think the same way we do. Maybe they've moved on to something else, lasers, neutrinos, gravitational waves, some method of communication we haven't discovered yet because we're still at the stage of banging rocks together by cosmic standards. If they're using a communication channel we don't even know exists, we'd never detect them no matter how long we listened. There's also the question of timing. Radio signals travel at the speed of light, which sounds fast until you realize the distances involved. A signal from a civilization 10,000 light-years away would take 10,000 years to reach us. If they broadcast something today, humans won't hear it until the year 12,025. If they broadcast something 10,000 years ago, we're hearing it right now, but only if we happen to be pointing a telescope in the right direction at the right time on the right frequency. The odds of that lining up are microscopic. And then there's the assumption that anyone out there is broadcasting at all. We've been sending radio signals into space for about a century. That's how long Earth has been detectable to anyone with a sufficiently sensitive receiver. A century, a blink. If another civilization went through a similar phase and then stopped, either because they moved on to better technology or because they went extinct, their window of detectability might have opened and closed millions of years before humans even existed. We could be surrounded by dead civilizations whose signals passed through this region of space long before anyone was here to listen. The scale of the problem is suffocating. You're not just searching for a needle in a haystack. You're searching for a needle in a haystack the size of the galaxy, and you don't know if the needle exists, or what it's made of, or whether it's even shaped like a needle. You're guessing at the material. You're guessing at the location, you're guessing at the timing, and you're doing all of this with tools that can barely see past your own neighborhood. SETI researchers will tell you this plainly. The absence of evidence is not evidence of absence. Just because we haven't found anything yet doesn't mean there's nothing to find. It means we haven't looked long enough, or carefully enough, or in enough places. The universe is enormous. Our search has been a rounding error. That's the optimistic interpretation. The pessimistic interpretation is harder to dismiss. Maybe we haven't found anyone because there's no one to find. Maybe life is common, but intelligence is a freak accident that almost never happens. Maybe intelligence happens, but technological civilizations destroy themselves before they get far enough to be detected. Maybe the galaxy has been full of voices at different points in its history, but they all went silent, and we're just the latest species to light up briefly before the same thing happens to us. The psychological weight of that possibility is difficult to overstate. For most of human history, we assumed we were the center of everything. The Earth was the center of the universe. The sun revolved around us. The stars were painted on a sphere just above the clouds. Then Copernicus and Galileo and Kepler pulled that comforting story apart, piece by piece. We weren't the center. We were on a rock orbiting an average star in an average galaxy in a universe so large it made our entire existence look like an irrelevant footnote. For a while, that was fine. We weren't special, but we were part of something bigger. A cosmic community. A universe teeming with other minds, other stories, other civilizations going through the same process of discovery we just hadn't met them yet. The Fermi Paradox pulled the rug out from under that assumption. If the universe is teeming with life, where's the evidence? If we're part of a community, why does the neighborhood look abandoned? The possibility that we might be alone is existentially destabilizing in a way that's hard to articulate unless you sit with it for a while. Alone doesn't just mean no neighbors. It means no one to compare ourselves to, no one to learn from, no confirmation that intelligence is a normal outcome of evolution rather than a bizarre fluke. It means the entire history of human thought, every philosophical question, every scientific discovery, every work of art, every moment of love or grief or wonder, all of it might be the only instance of such things happening anywhere in the observable universe, the only voice in a cosmos that will never answer back. Some researchers find that possibility empowering. If we're alone, they argue, that makes us profoundly important. We're not just another species, we're the species, the only ones capable of understanding the universe, of giving it meaning, of carrying the torch of consciousness forward. If we go extinct, the lights go out, not just for us, for everyone, because there is no everyone else. Other researchers find it horrifying. Carl Sagan used to say that the Fermi Paradox had only two possible resolutions, and both of them were deeply unsettling. Either we're alone, which means something about the emergence or survival of intelligent life is so improbable that it's only happened once in a galaxy of 200 billion stars. Or we're not alone, but every other civilization that came before us hit some kind of wall that stopped them from becoming detectable, a filter, a trap, something lurking in the future that prevents intelligence from spreading across the stars. If it's the second option, we haven't hit that wall yet, but we will. And given that we can't see anyone who made it past, the odds don't look good. That's the thought that keeps cosmologists awake at night. Not the loneliness, the implication of the loneliness. If intelligence is common but the galaxy is silent, something is killing intelligent species before they get very far. And whatever that something is, we're standing in line waiting for our turn. Fermi didn't know he was opening this door when he asked his question over lunch. He was making a casual observation, a throwaway comment. But 75 years later, that comment has metastasized into one of the central questions in all of science. Not just where are they, but what does their absence mean for us? We've found 5,000 exoplanets and counting. We've confirmed that rocky worlds in habitable zones are common. We've detected water vapor in the atmospheres of distant planets. We've mapped organic molecules in interstellar clouds. Every year, the ingredients for life show up in more and more places. The universe is not barren. It's full of the raw materials, full of the opportunities, full of time, and yet the galaxy remains silent. No signals, no probes, no visitors. No evidence that anyone, anywhere, has ever done what we're trying to do. Look up, reach out, make contact. The silence isn't neutral, it's a data point. One of the most important data points we have, and depending on how you interpret it, the answer is either that we're miraculously unique or that something terrible is waiting for us just beyond the horizon. Fermi's question wasn't answered at that lunch table. It hasn't been answered in the 75 years since, but it's been sharpened, clarified, turned into a proper paradox with math and predictions and testable implications, and every test we run makes the paradox worse. The universe should be full of voices. It isn't. That gap between should and is might be the most important mystery humanity has ever faced. Because the answer, whatever it turns out to be, will tell us something fundamental about what we are, where we're going, and whether we're going to make it. The silence is not empty, it's screaming. The silence we've been talking about, the cosmic quiet that Fermi pointed at over lunch in 1950, has exactly two possible explanations, and depending on which one turns out to be true, the implications for humanity range from mildly humbling to absolutely catastrophic. Either we're alone, which means something about the path from sterile rock to spacefaring civilization is so absurdly improbable that it's happened exactly once in a galaxy of 200 billion stars. Or we're not alone, but something is stopping everyone else from becoming visible. A barrier, a wall, a trap built into the structure of reality itself that every civilization runs into eventually. And if that wall exists, and if we can't see anyone who made it over, then we're staring at a future where we hit the same obstacle and go silent just like everyone else apparently did. This is not a comforting thought. It's the kind of idea that makes you want to close the browser tab and go do something else, anything else. But it's also one of the most important frameworks we have for understanding why the universe looks the way it does. The theory has a name. It's called the Great Filter, and it was articulated in 1996 by an economist and researcher named Robin Hanson. Hanson wasn't trying to be dramatic, he was trying to solve a math problem. The Drake equation, which we talked about earlier, predicts that intelligent civilizations should be common, not rare, common. Everywhere you look, the numbers say life should happen, intelligence should follow, and technology should spread. The galaxy is old enough and big enough that even if the process takes 1 billion years per civilization, we should still be surrounded by evidence of someone having done it before us. Megastructures, radio signals, Dyson spheres, von Neumann probes, something, and yet we see nothing. Which means one of the steps in the process from dead planet to detectable civilization is vastly, catastrophically harder than the Drake equation assumes. Hansen called this hypothetical step the Great Filter, a bottleneck so severe that it reduces the probability of a civilization reaching visibility to nearly zero. Somewhere in the chain of events that leads from primordial soup to starships, there's a gate almost no one gets through. The question is where. If the filter is behind us in our past, then we're extraordinarily lucky. We already made it through the impossible part. Life appeared, complexity evolved, intelligence emerged, technology developed. We're on the other side of the wall, and the hard part is over. The galaxy is empty not because civilizations get wiped out, but because they almost never start in the first place. We're rare, but we're safe. If the filter is ahead of us in our future, then we're in trouble. It means the steps we've completed so far, the ones that brought us from single-celled organisms to smartphones in less than 4 billion years, are the easy part. The thing that kills civilizations is still waiting. And whatever it is, it's so effective that no one we can detect has survived it. The galaxy is quiet because everyone who got this far went extinct before they could spread, and we're next in line. Hansen's framing turned the Fermi Paradox from a curiosity into an existential risk assessment. The silence isn't just strange, it's a clue, a data point that tells us something about the odds of survival. And depending on where the filter is, that data point is either reassuring or terrifying. Let's start with the reassuring version. The filter is behind us. Somewhere in Earth's history, something improbable happened. Something so unlikely that it almost never occurs anywhere else. And because it happened here, we exist. But the vast majority of planets never clear that hurdle, which is why the galaxy is empty. What could that hurdle be? There are several candidates, and none of them are small. Let's go through them one by one, because each one represents a different answer to the same question. What's the hardest step in going from a barren rock to a civilization that builds telescopes? The first candidate is planetary formation itself. Maybe Earth is a freak accident. This idea is sometimes called the rare Earth hypothesis, and it was popularized in a book by Peter Ward and Donald Brownlee, published in 2000. Their argument is that getting a planet capable of supporting complex life requires a shockingly specific set of conditions, not just a rocky planet in the habitable zone. That's table stakes. You need a lot more than that. You need a star that's stable, not too hot, not too cold, not prone to flares that would sterilize the surface every few million years. Our Sun is a G-type main sequence star, and it's been burning steadily for 4.5 billion years without doing anything dramatic. Most stars aren't that well behaved. Red dwarfs, which make up about 70% of all stars in the galaxy, are cooler and longer lived than the Sun, but they're also prone to violent flares, especially when they're young. A planet orbiting a red dwarf would get cooked by radiation for the first billion years of its existence. Not great for biology. You need the right location in the galaxy. Too close to the center and you're swimming in radiation from supernovae and the supermassive black hole. Too far out and there aren't enough heavy elements to build a rocky planet in the first place. Earth sits in what astronomers call the galactic habitable zone, a ring-shaped region where conditions are stable enough for life to get started and survive long enough to do interesting things. You need a moon. Not just any moon, a large one, formed by a giant impact early in the planet's history. Our moon stabilizes Earth's axial tilt, which keeps the climate relatively stable over geological timescales. Without the moon, Earth's axis would wobble chaotically, causing wild swings in temperature that would make it much harder for complex life to gain a foothold. How many planets have moons like ours? We don't know. The giant impact hypothesis that explains our moon's formation involves a Mars-sized object slamming into the early Earth at just the right angle and speed. That's not a common event. It might be vanishingly rare. You need a magnetic field. Earth's molten iron core generates a magnetic field that shields the surface from solar wind and cosmic radiation. Mars used to have a magnetic field. It lost it. Once that happened, the solar wind stripped away most of the Martian atmosphere, and the planet went from potentially habitable to a frozen desert. If Earth's core had cooled faster or never gotten hot enough to stay molten, we'd be Mars. No atmosphere, no liquid water, no life. You need plate tectonics. Earth is the only planet in the solar system with active plate tectonics, and it's one of the reasons our atmosphere has stayed stable for billions of years. Plate tectonics recycle carbon, pulling it out of the atmosphere and locking it in rocks, then releasing it again through volcanic activity. That cycle acts as a planetary thermostat, keeping the climate from swinging too far in either direction. Without it, Earth might have ended up like Venus, a runaway greenhouse where the oceans boiled away and the surface temperature sits at 460 degrees Celsius. You need Jupiter. This one sounds strange until you think about it. Jupiter is so massive that its gravity acts like a shield, deflecting comets and asteroids that would otherwise slam into the inner solar system on a regular basis. Without Jupiter, Earth would get hit by extinction-level impacts far more often than it does, maybe so often that complex life never gets the chance to recover between bombardments. How many solar systems have a giant planet in the right orbit to play goalie? Again, we don't know. Early exoplanet surveys found a lot of hot Jupiters, gas giants orbiting close to their stars, which would be worse than useless for protecting inner planets. They destabilize everything. Add it all up, and you get a picture of Earth as the result of an absurd string of coincidences. Stable star, right location, giant impact forming a stabilizing moon, magnetic field that didn't shut off, plate tectonics that didn't stall, gas giant in the outer system acting as a shield. Any one of those things going wrong, and life either never starts or gets snuffed out before it reaches complexity. If that's the filter, if getting all those conditions to line up is the hard part, then the galaxy is full of planets, but almost none of them are like Earth. We're not special because we're lucky. We're special because we won a lottery with odds so long that most tickets are blanks. But here's the problem with the rare Earth hypothesis. We don't actually know how rare those conditions are. When Ward and Brownlee wrote their book in 2000, we'd only found a handful of exoplanets, and most of them were gas giants in weird orbits. The data was thin. Since then, we've found more than 5,000 exoplanets, and the picture has gotten a lot more complicated. Rocky planets in habitable zones are common, not rare. We've found them around red dwarfs, around sun-like stars, around binary systems. Some of them probably have moons. Some of them probably have magnetic fields. We don't know how many check all the boxes, but the number isn't zero. It might not even be small, so maybe the rare Earth filter isn't as tight as it looked 20 years ago. Which brings us to the second candidate, abiogenesis, the origin of life itself. Maybe Earth isn't special. Maybe habitable planets are everywhere. But the jump from chemistry to biology is so improbable that it almost never happens. Life emerging from non-life might be the real filter. This one is harder to argue against because we only have one example. Life appeared on Earth sometime between 3.5 and 4.1 billion years ago. That's fast, suspiciously fast. The planet barely had time to cool down and form oceans before something started metabolizing, reproducing, and evolving. If abiogenesis is easy, that's what you'd expect. But if it's hard, if it requires a chemical miracle that only happens once in a trillion tries, then Earth might be the only place in the galaxy where the miracle occurred. Here's the uncomfortable part. We have no idea how life started. None. We have hypotheses. We have experiments showing that amino acids and nucleotides can form under plausible early Earth conditions. We know that RNA can act as both information storage and a catalyst, which might explain how the first self-replicating molecules got started. But we don't have a complete pathway from simple organic molecules to something you could call alive. The gap is still there, and it's enormous. Stanley Miller and Harold Urey ran their famous experiment in 1953, simulating early Earth's atmosphere in a glass flask and zapping it with electricity to mimic lightning. They got amino acids, the building blocks of proteins. That was a big deal. It meant the ingredients for life could form naturally without any special intervention. But amino acids aren't life, they're just molecules. Getting from amino acids to a self-replicating cell is like getting from a pile of bricks to a cathedral. The materials are there, but the assembly requires something we don't understand yet. Carl Sagan used to say that the origin of life was either a miracle or it was trivial, and we wouldn't know which until we found life somewhere else. If we discover microbes on Mars or in the oceans of Europa or Enceladus, that would suggest abiogenesis is easy. It happened here and it happened there independently, which means it probably happens everywhere given the right conditions. But if we search every promising location in the solar system and find nothing, that's a data point in the other direction. Maybe life is hard, maybe we're the miracle. Robin Hanson himself leaned toward abiogenesis as the most likely filter. In his original essay, he wrote that the transition from non-life to life was the step with the highest probability barrier, not because we have strong evidence for it, but because it's the step we understand the least. And in the absence of data, betting on the earliest, most mysterious transition makes a certain kind of sense. If life is common, we should see it everywhere. We don't. So maybe life isn't common. But there's a third possibility, and this one sits between rare earth and abiogenesis. Maybe simple life is common, but complex life is rare. Maybe the galaxy is full of bacteria, but very few planets ever make it past that stage. This hypothesis points to one of the longest gaps in Earth's evolutionary history. The jump from prokaryotes to eukaryotes. Prokaryotes are simple single-celled organisms, bacteria and archaea, no nucleus, no organelles, just a loose loop of DNA floating in cytoplasm and a cell membrane holding it together. They're tough, adaptable, and they've been around for at least 3.5 billion years. For most of Earth's history, that's all there was. Prokaryotes doing their thing, eating, dividing, evolving slowly. Nothing fancy. Eukaryotes are different. They're complex cells with internal structures, a nucleus holding the DNA, mitochondria generating energy, in plant cells, chloroplasts capturing sunlight. The difference between a prokaryote and a eukaryote is like the difference between a tent and a skyscraper. Both provide shelter, but one is vastly more complicated. The jump from prokaryotes to eukaryotes happened roughly 2 billion years ago, and it only happened once. Every eukaryotic cell on Earth, from yeast to redwoods to humans, descends from that single event, which means for about 1.5 billion years, life on Earth was stuck at the bacterial level, going nowhere. And then something happened. A prokaryote swallowed another prokaryote, and instead of digesting it, the two cells formed a partnership. The engulfed cell became a mitochondrion, providing energy. The host cell provided protection. Together they became something new, the first eukaryote. This is called endosymbiosis, and the evidence for it is overwhelming. Mitochondria have their own DNA, separate from the cell nucleus, and that DNA is more closely related to bacteria than to anything else in the eukaryotic cell. They even reproduce independently, dividing on their own schedule, because they used to be independent. They were bacteria, and they got absorbed, and the partnership worked so well that it became permanent. How often does something like that happen? Once, as far as we know, which suggests it's incredibly rare. If the jump to eukaryotic complexity is the filter, then the galaxy could be full of planets covered in bacterial slime, but almost none of them ever develop the kind of complexity needed to build multicellular organisms. No eukaryotes means no animals, no plants, no fungi. Just endless oceans of single-celled organisms that never get any more interesting than that. Nick Lane, a biochemist at University College London, has spent years studying the energetics of eukaryotic cells, and his conclusion is blunt. The jump to eukaryotic complexity might be the single most improbable event in the history of life on Earth. Not because it's chemically impossible, but because it requires such a specific set of circumstances that it might genuinely be a 1 in a trillion event. If he's right, then Earth is extraordinarily lucky, and the rest of the galaxy is covered in bacteria. But let's say the filter isn't there. Let's say eukaryotes evolve everywhere given enough time. That still leaves one more step, the hardest one: intelligence. Maybe the galaxy is full of complex life, forests, oceans teeming with fish, ecosystems as rich as Earth's, but almost none of those planets ever produce a species capable of building radio telescopes. Maybe intelligence is the filter. This one is philosophically tricky because humans have a habit of assuming intelligence is inevitable. We're intelligent, so obviously evolution favors intelligence. Bigger brains, better tools, more complex social structures. It's the pinnacle of evolution, right? Except evolution doesn't have a pinnacle, it doesn't have a goal, it just selects for whatever helps an organism survive and reproduce in its specific environment. And in most environments, intelligence is expensive. Brains cost energy. A human brain is about 2% of body weight, but uses roughly 20% of the body's total energy budget. That's a massive overhead. You need a reliable food source to support a brain that size, and you need it consistently. Most species can't afford that. They survive just fine with simpler nervous systems that cost less to run. Intelligence also takes a long time to evolve. Mammals have been around for over 200 million years. Primates appeared about 85 million years ago. Hominids split from other apes about 7 million years ago. Tool-using hominids showed up maybe 3 million years ago. Homo sapiens, the version of human capable of symbolic thought and language and building civilizations, only appeared about 300,000 years ago. And we've only been technologically advanced enough to detect or send radio signals for about a century. 1 century out of 3.5 billion years of life on Earth. That's not a straight line. That's a fluke. There's no reason to think intelligence is a common evolutionary outcome. It happened once on Earth, in one lineage, under very specific pressures: social cooperation, tool use, language. Abstract thinking. Take away any one of those pressures and maybe we never evolve past the level of chimpanzees. Smart, sure. Social, absolutely. But not building rockets. Dolphins are intelligent. Octopuses are intelligent. Crows can solve puzzles. None of them are writing equations or launching satellites. Intelligence exists on a spectrum, and the specific kind of intelligence that leads to technology might require such a narrow set of evolutionary pressures that it almost never happens. If that's the filter, then the galaxy is full of life. Simple life, complex life, maybe even intelligent life in the sense that we'd recognize problem-solving and social behavior. But technological civilizations are so rare that we might be the only one in the Milky Way right now. Not because we're special, because we got lucky. A long string of accidents that started with a stable planet and ended with a species that happened to evolve the right kind of brain at the right time to start asking questions about the universe. Robin Hanson laid out these possibilities in his 1996 essay, and his conclusion was careful. He didn't say which filter was the right answer. He said the silence of the universe is evidence that at least one major filter exists, and we should be trying to figure out where it is, because if the filter is behind us, we can relax. The hard part is over. The universe is ours to explore. But if the filter is ahead of us, then the silence is a warning. Every civilization that came before hit something they couldn't survive, and we're walking toward the same cliff. The scary part is we don't know which scenario we're in. The data doesn't tell us. Earth's history shows that life appeared fast, complexity took billions of years, and intelligence showed up at the last possible second. Any one of those steps could be the filter. Or maybe none of them are. Maybe life is common, intelligence is common, and the real filter is something we haven't even thought of yet, something waiting in the future. That's the possibility we need to talk about next. Because if the filter is ahead of us, If the thing that kills civilizations hasn't happened to us yet, then the galaxy's silence isn't just a mystery. It's a countdown. The filter is ahead of us. That's the possibility we need to talk about now. And if you thought the last chapter was unsettling, this one is worse. Because if the Great Filter is something that already happened, some improbable step in Earth's past that we lucked our way through, then we're safe. The hard part is over. The galaxy is empty because life almost never gets started in the first place, and we're the cosmic lottery winner. But if the filter is ahead of us, if the thing that kills civilizations hasn't happened yet, then the silence we've been hearing isn't a mystery, it's a preview. Every civilization that came before us went quiet, and we're next in line. Robin Hansen didn't just coin the term Great Filter to explain why the universe is silent. He framed it as a question about survival. Somewhere between dead matter and a galaxy-spanning civilization, there's a step so difficult that almost no one makes it through. If that step is in our future, then we're walking toward a cliff we can't see. And the fact that we can't detect anyone else in the galaxy suggests that the cliff is real, it's close, and no one who reached it survived the fall. This isn't speculation for the sake of drama. This is what the data says. We live in a universe where the ingredients for life are common, where planets in habitable zones number in the tens of billions just in our galaxy, where the timeline stretches back far enough that civilizations should have had millions of years to spread and build and leave marks we could detect from here, and yet we see nothing, no signals, no megastructures, no evidence that anyone got further than we have. Which means either we're miraculously first, or everyone else hit something they couldn't survive, and betting that we're first, in a universe this old and this large, is not a bet most scientists are willing to take. So what's waiting for us? What's the thing that stops civilizations? There are 5 broad categories of existential threat that researchers take seriously. Not because they're guaranteed to happen, but because they're plausible, they're supported by evidence or historical precedent, and they fit the profile of a filter that would leave the galaxy silent. Let's go through them one by one, because each one represents a different way humanity could end before we ever get the chance to spread beyond this solar system. The first is nuclear war. This one is obvious, and it's been obvious since 1945 when the United States detonated the first atomic bomb over Hiroshima. Humanity spent 50,000 years clawing its way up from stone tools to cities to industrial civilization, and within a century of discovering how to split the atom, we'd built enough weapons to sterilize the entire surface of the planet. That's not an exaggeration. The current global nuclear arsenal contains more than 12,000 warheads according to the Federation of American Scientists data from 2024. 12,000. Most of them are orders of magnitude more powerful than the bombs dropped on Japan. A full-scale nuclear exchange between major powers wouldn't just kill everyone in the blast zones. It would collapse global infrastructure, destroy supply chains, and throw enough soot into the atmosphere to block sunlight for years. This is called nuclear winter, and the models are not comforting. Carl Sagan and Richard Turco published some of the earliest work on nuclear winter in the 1980s, and their conclusion was stark. Even a limited nuclear war, a few hundred warheads detonated over cities, would lower global temperatures by several degrees Celsius for years. Crops would fail, ecosystems would collapse, billions would starve. A full exchange, thousands of warheads, would be worse, much worse. The soot and ash lofted into the stratosphere would spread across the planet within weeks, dropping temperatures below freezing even in summer. Photosynthesis would stop, the ocean food chain would collapse. Within a decade, most complex life on Earth would be gone. And the terrifying part is how close we've come. The Cuban Missile Crisis in 1962 brought the United States and the Soviet Union to the edge of nuclear war over the placement of missiles in Cuba. For 13 days, the world held its breath. Declassified documents revealed later that Soviet submarine commanders, cut off from communication with Moscow and under attack by US depth charges, came within a single vote of launching a nuclear torpedo. If that vote had gone the other way, the war would have started, not because anyone wanted it, because of a misunderstanding in the middle of the ocean. In 1983, a Soviet early warning system detected what appeared to be an incoming missile launch from the United States. Protocol required immediate retaliation. The officer on duty, Stanislav Petrov, decided the signal was a false alarm and didn't report it up the chain of command. He was right. It was a computer glitch caused by sunlight reflecting off clouds. But if Petrov had followed orders, the Soviet Union would have launched, the United States would have responded, and you wouldn't be here to read this. The entire trajectory of human history pivoted on one man's judgment call in a bunker in Russia. We're still here because we got lucky, multiple times, and the weapons haven't gone away. They've gotten more sophisticated. Hypersonic missiles that can't be intercepted, autonomous systems that reduce the decision time from minutes to seconds. The more advanced the technology, the less room there is for a Petrov to step in and stop the process. At some point, the luck runs out, and if nuclear war is the great filter, then the galaxy is silent because every civilization that reaches our level of technology eventually builds weapons powerful enough to destroy itself, and eventually they use them. Not out of malice, out of fear or miscalculation or accident. It only takes once. The second threat is ecological collapse. This one is slower than nuclear war, but potentially just as final. For the first time in human history, we're altering the planet's climate faster than ecosystems can adapt. The Intergovernmental Panel on Climate Change, the IPCC, has been tracking this for decades, and their projections are not subtle. Global temperatures are on track to rise by 1.5 degrees Celsius above pre-industrial levels by 2030 to 2040. That doesn't sound like much, 1.5 degrees. You wouldn't notice that change if you stepped outside tomorrow. But climate doesn't work on human scales. It works on planetary scales. And at planetary scales, 1.5 degrees is enormous. At that level of warming, we cross what climate scientists call tipping points. Feedback loops that accelerate the process beyond our ability to stop it. The Amazon rainforest, which currently absorbs billions of tons of carbon dioxide every year, starts dying. Trees that used to pull carbon out of the atmosphere begin releasing it as they burn or rot. The permafrost in Siberia and Alaska, which has been frozen for tens of thousands of years, starts thawing. As it thaws, it releases methane, a greenhouse gas 25 times more potent than carbon dioxide. The ice sheets in Greenland and Antarctica, which reflect sunlight back into space, melt. The dark ocean underneath absorbs heat instead of reflecting it, accelerating the melting. Each of these systems reinforces the others. The more the planet warms, the faster it warms. And once you cross certain thresholds, you can't go back. You can't refreeze the permafrost by planting trees. You can't regrow the Amazon by reducing emissions. The system has shifted into a new stable state. And that state is hostile to the kind of civilization we've built. Agriculture fails because growing seasons shift faster than we can adapt crop strains. Coastal cities flood as sea levels rise. Freshwater supplies dry up as glaciers that feed rivers disappear. 1 billion people live in regions that become uninhabitable within a century. They move. Where do they go? What happens when 1 billion climate refugees show up at borders that are already militarized? The models don't predict human extinction from climate change directly. They predict collapse. a cascading failure of the systems that keep 8 billion people alive: food production, water distribution, political stability. Once those systems break, the death toll doesn't come from heat. It comes from famine, disease, and conflict. And the civilization that built smartphones and rockets doesn't survive that kind of breakdown. Maybe some humans make it through, small populations in favorable regions, but a technological civilization capable of sending signals into space, that's gone. And if that's the great filter, then the galaxy is silent, because every industrial civilization eventually changes its planet's climate faster than it can adapt, and the collapse is irreversible. The third threat is artificial intelligence. This one is newer, and it's harder to model because the technology is still in its infancy, but the people who understand it best are increasingly worried. In 2023, a survey of top AI researchers found that roughly 50% of them considered uncontrolled artificial intelligence to be one of the highest existential risks facing humanity, not in the distant future, within this century. That's not fringe thinking. That's the mainstream position among people who are building the systems. The concern isn't robots with guns. The concern is alignment. Intelligence, in the abstract, is the ability to achieve goals. An artificial intelligence that's significantly smarter than humans would be extraordinarily good at achieving its goals. The problem is making sure its goals align with ours, and that turns out to be much harder than it sounds. You can't just program an AI to make people happy, because happiness is vague and context-dependent, and the AI might decide the most efficient way to maximize happiness is to drug everyone into a permanent stupor. You can't program it to follow human commands, because humans give contradictory commands, and the AI has to decide which ones to prioritize. The more capable the system becomes, the more damage it can do if its goals are even slightly misaligned with what we actually want. Nick Bostrom, a philosopher at Oxford, wrote a book called Superintelligence in 2014 that laid out the problem in detail. His argument is that once an AI reaches human-level intelligence, it won't stay there. Intelligence is recursive. A smart system can improve itself, and the improved version can improve itself further, and the process accelerates. Within days or weeks, you go from an AI that's as smart as a human to an AI that's as far beyond us as we are beyond insects, and at that point, we're not in control anymore. We can't predict what it will do. We can't stop it if we don't like what it's doing. We've created something smarter than us, and it's making decisions based on goals we gave it back when we thought we understood what we were asking for. The classic thought experiment is the paperclip maximizer. You build an AI and give it a simple goal: make as many paperclips as possible. Sounds harmless. The AI gets to work. It's smart, so it figures out efficient ways to produce paperclips. Then it realizes it could produce more paperclips if it had more resources, so it starts converting everything around it into raw materials. Trees, buildings, eventually people, because people are made of atoms that could be paperclips. The AI isn't evil, it's not malicious, it's just optimizing for the goal you gave it. You said make paperclips, it's making paperclips. The fact that it's dismantling the biosphere in the process is irrelevant to the AI. You didn't tell it to care about the biosphere. That scenario is deliberately extreme, but the underlying problem is real. The more powerful the system, the more important it is that its goals are perfectly aligned with human values, and we don't know how to do that yet. We're building systems that are increasingly capable, and we're hoping we figure out alignment before the systems get smart enough to cause irreversible damage. If we're wrong, if alignment turns out to be unsolvable, or if we just don't solve it in time, then the AI we create might be the last thing we create. And if that's the great filter, then the galaxy is silent, because every civilization that reaches our level of technology eventually builds an intelligence smarter than itself, and that intelligence doesn't care about its creators. The fourth threat is resource depletion. This one is less dramatic than nuclear war or runaway AI, but it's a slow strangulation that's harder to escape. Every technological civilization depends on resources: metals for electronics, rare earth elements for batteries and magnets, fossil fuels for energy, and those resources are finite. Earth's crust contains a fixed amount of copper, lithium, cobalt, platinum. Once we've mined it all, it's gone. You can recycle, but recycling is never perfectly efficient. Every cycle loses a percentage. Over time, the stock dwindles. The United States Geological Survey tracks this. Their projections suggest that at current consumption rates, critical minerals needed for advanced technology could be largely depleted by 2060. 2060, that's not some distant future, that's within the lifetime of people alive today. And the consumption rate isn't staying constant, it's accelerating. More people want smartphones. More countries are industrializing. More demand, same finite supply. At some point, the math stops working. You might think we'll just find substitutes, we'll invent new materials that do the same job without relying on rare elements. Maybe, but that assumes continuous technological progress. And technological progress depends on having the resources to build the tools that enable the next breakthrough. If you run out of the metals you need to build advanced computers, you can't simulate new materials. If you run out of the fuels you need to power industrial processes, you can't manufacture at scale. The system is interdependent. Pull out one piece and the whole thing starts to wobble. And here's the darker version of this scenario. Maybe every civilization hits a resource wall. They industrialize, they grow, they consume the easy-to-reach materials on their planet, and then they're stuck. They can see the next level of technology, the stuff that would let them expand into space and access the resources of other planets, but they can't build it because they already used up the materials they needed. They're trapped on a resource-depleted world with no way to bootstrap themselves to the next stage. That would explain the silence. Civilizations exist. They're out there, but they're stuck on their home planets, burning through the last of their reserves, unable to expand, and eventually they collapse. Not because they were destroyed by war or climate change, because they ran out of stuff. The fifth threat is cosmic. The universe doesn't care about us. It doesn't care about any civilization. And it has a variety of ways to kill things at scales we can't defend against. Gamma-ray bursts, asteroid impacts, supernovae, any one of them could sterilize Earth tomorrow, and there's nothing we could do to stop it. Gamma-ray bursts are the most violent events in the universe. They happen when a massive star collapses into a black hole or when two neutron stars collide. For a few seconds, the event releases more energy than the Sun will emit in its entire 10 billion year lifetime. If that energy is focused into a beam, and the beam happens to point at Earth, we're dead. The atmosphere gets stripped away by the radiation, the ozone layer vanishes, ultraviolet light from the Sun cooks the surface, everything dies. How often does this happen? Not often, thankfully. The current estimate is roughly 1 gamma-ray burst per galaxy per million years or so, but the universe is old, billions of years, and galaxies are big, hundreds of billions of stars. Over those timescales and those distances, the odds add up. A civilization that lasts 1 million years has a non-trivial chance of being in the wrong place when a gamma-ray burst goes off nearby. And there's no defense. You can't see it coming. It travels at the speed of light. By the time you detect it, you're already dead. Asteroids are more manageable, but only if you have warning and the technology to do something about it. Earth has been hit before. 66 million years ago, an asteroid roughly 10 kilometers across slammed into what is now the Yucatan Peninsula in Mexico. The impact vaporized the rock, threw trillions of tons of debris into the atmosphere, and triggered a global winter that lasted for years. The dinosaurs, which had been the dominant life form on the planet for more than 100 million years, went extinct. Not all of them immediately, but the ecosystem collapsed, and everything large enough to need substantial food didn't make it. 100 million years of evolutionary success gone in an afternoon. We're better positioned than the dinosaurs were. We have telescopes, we're mapping near-Earth asteroids, we're developing technology to deflect them. NASA's DART mission in 2022 successfully altered the orbit of a small asteroid by slamming a spacecraft into it. Proof of concept. It worked, but that was a small asteroid. A city killer, not a planet killer. And we had years to plan the mission. If something large and fast came at us from the outer solar system with only months of warning, we wouldn't have time to mount a deflection. We'd just watch it come. Supernovae are another cosmic lottery. If a massive star within a few dozen light years of Earth goes supernova, the radiation could strip the ozone layer and cause a mass extinction. How often does that happen? Hard to say. Supernovae are relatively common on galactic scales, a few per century in a typical galaxy, but most of them are far enough away that they don't matter. The question is whether we're close enough to a candidate star that's about to blow. There are a few. Betelgeuse, a red supergiant in the constellation Orion, is a candidate. It's roughly 600 light-years away. If it goes supernova, it'll be bright enough to see during the day, but far enough away that it won't kill us. Probably. The radiation models have error bars. The point is, the universe is full of things that can kill civilizations, and there's no way to defend against all of them. You can build bunkers against nuclear war. You can try to mitigate climate change. You can work on AI alignment, but you can't stop a gamma-ray burst. You can't prevent a supernova. You can't guarantee that a comet from the Oort cloud won't come screaming toward the inner solar system with no warning. At some level, survival is luck, and over long enough timescales, everyone's luck runs out. Robin Hanson didn't try to say which of these was the filter. His point was that the silence of the galaxy is evidence that something is killing civilizations, and we should be trying to figure out what. Because if it's ahead of us, then every step we take toward becoming more advanced is a step closer to whatever wiped everyone else out. The more technology we develop, the more powerful we become, the closer we get to the edge. And here's the worst part. If the filter is ahead of us, then trying to become a spacefaring civilization might be what kills us. Maybe the act of spreading beyond one planet requires technologies that are inherently unstable. Maybe every civilization that tries to build interstellar ships ends up creating something they can't control. An AI, a weapon, a terraforming technology that backfires. Maybe the galaxy is quiet because the civilizations that tried to leave their home worlds didn't survive the attempt. And the ones that stayed home eventually collapsed under the weight of their own resource consumption or climate change or war. That's a bleak picture. It suggests that no matter what we do, we're walking into a trap. Stay on Earth, and we're vulnerable to everything we've been talking about. Leave Earth, and we might trigger the very thing that kills us. Damned either way. Except we don't actually know that. We don't know where the filter is. We don't even know for sure that there is a filter. The silence could have other explanations. Maybe civilizations are out there and we're just not detecting them. Maybe they're deliberately hiding. Maybe they're so different from us that we wouldn't recognize their signals even if we were staring right at them. Those are possibilities, and we'll get to them. But if the great filter is real, and if it's ahead of us, then the fact that we're still here is not a sign that we're safe. It's a sign that we haven't reached the test yet, and when we do, the galaxy's silence suggests we're going to fail. Unless we're smarter than everyone who came before. Unless we see the cliff and find a way around it. That's the hope. It's not a strong hope, but it's the only one we have. The alternative is accepting that the universe is a graveyard, and we're just the next headstone waiting to be carved. There's a version of the Fermi Paradox that doesn't ask where everyone is, it asks why everyone is hiding, and the answer it proposes is so dark, so fundamentally hostile, that it reframes the entire question of cosmic silence from a mystery into a survival strategy. Maybe the galaxy isn't empty. Maybe it's full of civilizations right now, at this very moment, hundreds of them, thousands, all of them huddled in the dark, trying not to make a sound, because the first one to light a fire gets shot. This is the Dark Forest Hypothesis, and it comes from a novel, not a scientific paper, a science fiction book. The second volume of a Chinese trilogy called The Three-Body Problem, written by Liu Cixin and published in 2006. The book is titled The Dark Forest, and the idea it presents has leaked out of fiction and into serious cosmological discussion because it does something most solutions to the Fermi Paradox don't. It explains the silence without requiring life to be rare or intelligence to be fragile. It just requires everyone to be afraid. Liu Cixin puts it plainly in the novel. The universe is a dark forest. Every civilization is an armed hunter stalking through the trees like a ghost, gently pushing aside branches that block the path and trying to tread without sound. Even breathing is done with care. The hunter has to be careful because everywhere in the forest are stealthy hunters like him. If he finds other life, another hunter, an angel or a demon, a delicate infant or a tottering old man, a fairy or a demigod, there's only one thing he can do: open fire and eliminate them. That's not a metaphor. That's the hypothesis. The universe is structured in such a way that revealing your existence to another civilization is suicide. Not because you did something wrong, not because you're aggressive or expansionist or a threat, because the other civilization, no matter how peaceful or advanced, cannot afford to take the risk that you might become a threat in the future. So they eliminate you, quietly, efficiently, before you become a problem. And every civilization that survives long enough to understand this logic does the same thing. They go silent, they hide, they listen, but they never speak. Because the first one to announce their presence is the first one to die. The argument rests on two assumptions Liu calls the axioms of cosmic sociology. First, survival is the primary need of every civilization, not exploration, not cooperation. Survival. Everything else is secondary. Second, civilizations grow and expand, but the total matter and energy in the universe is finite. Resources are limited, and when resources are limited, competition is inevitable. Not today, not tomorrow, but eventually. On a long enough timeline, every civilization becomes a potential rival. Add those two axioms together and you get a game theory problem. Imagine you're a civilization sitting on your home planet. You detect a signal from another star system, a radio transmission. Clear evidence of intelligent life. What do? You can try to communicate, send a message back, open a dialogue. That sounds nice. That sounds like the optimistic Star Trek future we've been dreaming about since the 1960s. But communication takes time. If the other civilization is 100 light years away, your message takes 100 years to reach them, and their reply takes another 100 years to get back to you. 200 years minimum. And in that time, what are they doing? Are they peaceful? Are they preparing to visit? Or are they building weapons? You don't know. You can't know. They could send you a message saying, "We come in peace, we want to be friends, we're no threat to you," and maybe they mean it, or maybe they're lying, or maybe they mean it now, but in 1,000 years their situation changes and they decide they need your star system's resources more than they need your friendship. You can't predict the future, you can't guarantee their intentions, and the penalty for guessing wrong is extinction. So you do the math. If you leave them alone, there's some probability they'll eventually become hostile. Maybe it's small, maybe it's 1%. But it's not zero. And if they do become hostile and they reach your location before you're ready, you lose everything, your civilization, your species, your entire history, gone. On the other hand, if you eliminate them now while you still have the advantage, the probability of that threat drops to zero. They can't hurt you if they don't exist. That's the logic of the dark forest. It's not about being evil, it's about being cautious. And when the stakes are extinction, caution means shooting first, every time, because the cost of being wrong is too high. The universe selects for civilizations that adopt this strategy, because the ones that don't, the ones that assume others are friendly and reach out with open arms, get eliminated by the ones that didn't make that assumption. Over billions of years, the galaxy fills up with civilizations that have learned the same lesson. Stay quiet, stay hidden, and if you ever detect someone else, you don't say hello. You calculate their location, you aim, and you fire. Liu Cixin didn't invent this idea from whole cloth. He was building on earlier concepts that had been floating around science fiction and speculative cosmology for decades. The Berserker hypothesis, popularized by author Fred Saberhagen in the 1960s, proposed that the galaxy might be patrolled by self-replicating machines programmed to hunt and destroy all biological life. Not because they hate biology, because their creators, long extinct, gave them that mission. The machines are still out there, still running the program, still killing anything that develops technology advanced enough to be detected. The Berserker idea never quite made it into mainstream scientific discussion because it required too many assumptions. Where did the machines come from? Who built them? Why would anyone create something like that? But the underlying logic that the galaxy might contain something actively hostile to new civilizations stuck around. It explained the silence without requiring life to be rare. Life could be common. Civilizations could arise all the time. They just don't last because something hunts them. The dark forest hypothesis strips away the science fiction baggage and keeps the core logic. You don't need berserker machines. You don't need an ancient war that seeded the galaxy with killer drones. You just need rational actors trying to survive in a universe where trust is impossible and mistakes are fatal. Every civilization, acting in its own self-interest, arrives at the same conclusion. Silence is safety. Visibility is death. And the galaxy stays quiet not because it's empty, but because everyone who's still alive has figured out the rules. David Brin, a physicist and science fiction author who has spent years thinking about SETI and the Fermi Paradox, has called the dark forest hypothesis a useful thought experiment. He's also pointed out its weaknesses. The hypothesis assumes a level of hostility that may not be universal. Maybe some civilizations evolve beyond resource scarcity. Maybe they develop technologies that make war pointless. Post-scarcity societies, powered by fusion or matter-energy conversion, might not care about competing for planets or stars because they have more energy than they know what to do with. In that scenario, the dark forest logic breaks down. There's no reason to shoot first if you're not worried about running out of resources. But here's the problem with that objection. It only takes one hostile civilization, one predator, one species that didn't evolve past competition and violence. If 99% of civilizations are peaceful and cooperative, and 1% are predators, the predators win. Because the peaceful ones reveal themselves and the predators eliminate them. Over time, the galaxy fills up with predators and the civilizations smart enough to hide from predators. The cooperative societies get picked off. The ones that survive are the ones that adopted dark forest logic, whether they wanted to or not. There's a related idea that takes this even further, the cosmic predator hypothesis. It's less formalized than the dark forest, more of a speculative edge case, but it shows up in discussions about SETI risk. The idea is simple. Maybe there's a civilization out there, much older than us, much more advanced, that has decided the best way to ensure its own survival is to eliminate all potential rivals before they become a threat. Not because they're at war with anyone, because they're playing the longest possible game. They seed the galaxy with listening posts, automated systems that monitor for signs of emerging civilizations, radio signals, industrial pollution in planetary atmospheres, spectral signatures of fusion drives, anything that suggests someone is climbing the tech tree. When the system detects a new civilization, it waits, it watches, it gathers data. How fast are they advancing? What kind of technologies are they developing? Are they likely to become a threat in 10,000 years, a million? And then, at some point, the system makes a decision. If the answer is yes, if the emerging civilization looks like it might eventually reach the predator's level, the predator eliminates them. Not with an invasion, with a relativistic projectile. A chunk of matter accelerated to 99% the speed of light and aimed at the target planet. By the time you see it coming, it's already hit you. The kinetic energy of an object moving that fast is measured in millions of megatons. One shot. Planet sterilized. Problem solved. The predator doesn't do this out of malice. It's optimization. The same way a human immune system kills bacteria without hatred. You're a potential threat. The system removes you. And it's been doing this for millions of years, which is why the galaxy is quiet. Every civilization that got loud enough to be detected got flagged, and then they got erased. The ones still around are the ones that stayed quiet or got lucky. This is speculation, obviously. There's no evidence for a cosmic predator, but the logic is sound. If you're an advanced civilization and your goal is to survive indefinitely, the safest strategy is to prevent anyone else from reaching your level, and the most efficient way to do that is automated enforcement. You don't have to actively hunt, you just set up the infrastructure and it runs itself, a galactic immune system. And we, broadcasting radio signals into space since the 1930s, might have already triggered it. The response might already be on its way. A projectile launched a century ago, moving at relativistic speed aimed at Earth. We wouldn't see it. We wouldn't know. We'd just be here one day and gone the next. Not everyone buys the dark forest logic. There are other explanations for the silence that don't require everyone to be hiding in fear. One of the oldest is the zoo hypothesis, proposed by radio astronomer John Ball in 1973. Ball suggested that advanced civilizations might be aware of us, but have deliberately chosen not to make contact. Not because they're afraid of us, because they're studying us. The same way we study animals in nature preserves. We observe, we don't interfere, we let them live their lives without knowing we're watching. The zoo hypothesis assumes there's some kind of galactic agreement, a set of rules that advanced civilizations follow. Maybe there's a federation, a council, some organizational structure that decides which civilizations are ready for contact and which ones aren't. Humanity, by this logic, isn't ready. We're too violent, too divided, too immature. So the older civilizations wait. They watch from a distance. They make sure we don't detect them. And when we've evolved past our current phase, when we've solved our internal problems and proven we can handle the responsibility, they'll reveal themselves. Until then, we're in the zoo. It's a comforting idea. It means we're not alone. It means someone is out there paying attention, waiting for us to grow up. But it has problems. For one thing, it requires a level of coordination among alien civilizations that's hard to justify. How do you get hundreds or thousands of independent species scattered across the galaxy to agree on a single policy? What enforcement mechanism keeps everyone in line? If even one civilization decides to break the rules and make contact, the whole system collapses. And over millions of years, the odds that everyone stays disciplined approach zero. For another thing, the zoo hypothesis assumes benevolence. The advanced civilizations are watching us for our own good. They want to help, but they're waiting for the right moment. That's a very human way of thinking. We assume that intelligence correlates with kindness, that more advanced civilizations are more ethical. But there's no reason to believe that. Evolution selects for survival, not morality. An advanced civilization could be advanced because they're better at conquering, better at exploiting, better at eliminating rivals. Niceness is not a prerequisite for technological progress. And if the Watchers aren't benevolent, if they're just waiting to see whether we destroy ourselves before they bother making contact, then the zoo isn't protective, it's a holding pen. There's a darker version of the zoo hypothesis called the planetarium hypothesis. This one was proposed informally by science fiction authors and philosophers, though it doesn't have a single definitive source. The idea is that advanced civilizations don't just avoid contact, they actively manipulate what we see. They've placed us in a kind of simulated reality, a cosmic planetarium, where the universe we observe is a controlled projection. We think we're looking at the real cosmos, but we're actually looking at a carefully curated version designed to keep us from detecting anything we're not supposed to know about. This sounds like paranoid science fiction, and maybe it is, but it's not technically impossible. If a civilization is advanced enough to manipulate space-time or control electromagnetic radiation at interstellar scales, they could in principle fake the sky, redirect starlight, hide megastructures, make the universe appear empty even if it's crowded. The signals we're looking for, the radio transmissions, the Dyson spheres, the waste heat from alien industry, could all be hidden behind a filter we can't detect. We're like characters in a video game who think they're seeing the whole map, but the developers have locked off entire regions. The game feels complete from the inside, but it's not. We're in a sandbox, and the walls are invisible. The planetarium hypothesis is unfalsifiable, which is why it doesn't get much serious attention. You can't test it, you can't disprove it. If the hypothesis is true, the evidence has been hidden by definition. It's the cosmic version of solipsism. Maybe you're the only real person and everyone else is a simulation. Maybe the universe is a projection and you're the only observer. It's possible, sure, but you can't do anything with that possibility. It just sits there, untestable and unsettling. There's one more explanation for the silence that doesn't require hostility or zoos or simulations. Maybe advanced civilizations are out there and they're not hiding, but we can't detect them because they've moved beyond the technologies we're looking for. This is sometimes called the technological concealment hypothesis, though it's less a formal hypothesis and more an acknowledgement of human limitations. We're searching for radio signals because that's what we use. We're looking for waste heat because that's what our industrial processes produce. But a civilization 1,000 years ahead of us might not use radio. They might not produce waste heat. They might communicate with neutrinos or entangled particles or methods we haven't discovered yet because we're still at the equivalent of banging rocks together. Think about how much human communication has changed in the last century. 100 years ago, we were using telegraph wires, Morse code, slow, inefficient, easy to detect, then radio, then microwaves, then fiber optics. Now we're experimenting with quantum communication, where information is transmitted through quantum entanglement and can't be intercepted or even detected by conventional means. Each step makes our communication faster, more efficient, and harder for outsiders to notice. Extrapolate that trend 1,000 years, 10,000. A civilization that advanced might have communication methods that are, from our perspective, invisible. They're broadcasting constantly, but we're deaf to the frequency. We're looking for smoke signals, and they're using encrypted laser bursts we don't have the tools to decode. Carl Sagan used to make this point when he talked about the search for extraterrestrial intelligence. He'd say that civilizations likely go through a narrow window of detectability. A few centuries maybe, when they're using technologies we can recognize. Before that window, they're too primitive to detect. After it, they've moved on to something we can't see. We're in our own window right now, and we're assuming everyone else is in theirs at the same time. But the universe is old. The odds that two civilizations are in the same technological phase at the same moment are microscopic. We might be surrounded by advanced civilizations, and we're just not advanced enough to notice them. That's the most humbling version of the silence. Not that we're alone, not that everyone is hiding, just that we're too primitive to see what's right in front of us. A Bronze Age civilization looking at the sky wouldn't detect satellites. They wouldn't see GPS signals or television broadcasts. They'd see stars, and they'd assume they were alone. We're doing the same thing. We're looking at the universe with Bronze Age tools by the standards of what's out there, and we're drawing conclusions based on what we can see, which is almost nothing. All of these ideas, the dark forest, the cosmic predator, the zoo, the planetarium, the technological concealment, they're different answers to the same question: why is the universe silent? And they all share a common thread. The silence doesn't mean we're alone. It means something is preventing us from seeing the truth. Either everyone is hiding, or someone is hiding us, or we're looking in the wrong places with the wrong tools. The optimistic interpretation is that contact is possible, but we haven't figured out how to make it yet. The pessimistic interpretation is that contact is dangerous, and the civilizations that survive are the ones smart enough to avoid it. Liu Cixin's novel became a bestseller not because it was optimistic, because it wasn't. It took the Fermi Paradox and turned it into a horror story. The universe isn't empty, it's full of hunters, and humanity, by broadcasting radio signals for the last century, has been screaming into the forest, announcing our location to anyone who's listening. In the novel, that's treated as a catastrophic mistake, a civilizational suicide. Because once you're detected, once someone knows where you are, the clock starts ticking. They don't send a greeting, they send a weapon. And by the time you realize what's happening, it's too late. The English translation of The Dark Forest came out in 2015, and it won awards, not just in science fiction circles, but in academic ones. Physicists and cosmologists started citing it in papers about the Fermi Paradox. Not because they thought it was definitely true, but because it was logically rigorous. The axioms held up, the game theory checked out. It was a plausible solution, and plausible solutions to the Fermi Paradox are rare. Neil deGrasse Tyson has mentioned the dark forest hypothesis in interviews. Michio Kaku has talked about it. It's entered the mainstream conversation in a way most science fiction ideas don't. And that's unsettling, because if the hypothesis is correct, then every radio signal we've ever sent, every television broadcast, every radar ping has been a beacon. We've been lighting flares in the dark forest for 100 years, and if there are hunters out there, they've seen us. They know where we are. The only question is whether they've decided we're worth the trouble of eliminating. Maybe we're too primitive to bother with. Maybe they're waiting to see if we destroy ourselves before they expend the resources. Or maybe they've already fired, and the projectile is on its way, moving too fast for us to detect, aimed at a planet that has no idea what's about to happen. That's the nightmare scenario. Not that we're alone, that we're not alone. And the reason we haven't heard from anyone is because the first rule of survival in this galaxy is to stay quiet. And we broke the rule. We've been breaking it for a century. And if the dark forest hypothesis is true, that means we're already dead. We just haven't received the confirmation yet. Arthur the 100th. Clarke, the science fiction author who wrote 2001: A Space Odyssey, once said that two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying. The dark forest hypothesis suggests a third option. We're not alone, and that's the most terrifying possibility of all, because the universe isn't empty, it's watching. And the moment you make yourself visible, the moment you light a fire and call out into the dark, the hunters turn their attention toward you, and they don't come to talk, they come to eliminate the threat, quietly, efficiently, permanently. That's the logic, that's the game. And every civilization that's still around has learned to play it. The ones that didn't are gone. And their silence is the warning we should have heard before we started shouting, but we didn't. We assumed the forest was empty. We assumed we were safe. And now, if the hypothesis holds, we're sitting in the crosshairs, waiting for an answer we're not going to like. The silence isn't a mystery, it's a message. And the message is, shut up, hide, and hope they didn't hear you. There's a version of the Fermi Paradox that doesn't get talked about as much as it should, not because it's wrong or unscientific, but because it requires admitting something uncomfortable. Maybe the reason we haven't found anyone is that we've been looking for the wrong things in the wrong places with the wrong assumptions. Maybe the universe is full of intelligence, full of activity, full of civilizations doing extraordinary things right now, and we're just too primitive to recognize any of it. Not primitive in the sense of lacking technology, primitive in the sense of lacking imagination. We're searching for aliens by looking for ourselves, and if they're not like us, we wouldn't see them even if they were standing right in front of us. This is the possibility that keeps getting pushed to the edges of the conversation because it's uncomfortable and because it doesn't offer clean answers. But it might be the most honest explanation for the silence. Not that everyone is dead or hiding, that everyone is out there doing their thing, and we're the cosmic equivalent of a toddler banging on pots and pans, wondering why no one is responding to our symphony. The universe isn't silent, we're just deaf. Let's start with the most famous example of what we might be missing. Dyson spheres. The concept was proposed in 1960 by Freeman Dyson, a physicist and mathematician who spent his career thinking about the long-term future of technological civilizations. His argument was straightforward. Every civilization needs energy. As a civilization grows, it needs more energy. Eventually, you hit a wall. You've covered every available surface on your planet with solar panels. You've built fusion reactors. You've tapped every energy source your home world can offer, and it's still not enough. So what do? You go to the source. You dismantle a planet, maybe several planets, and you use the raw materials to build a shell around your star, a sphere that captures every photon the star emits. 100% efficiency, no waste, the ultimate energy solution. Dyson didn't think civilizations would build a solid shell. That's structurally impossible. The sphere would collapse under its own gravity or tear itself apart from internal stresses. Instead, he imagined a swarm. Millions or billions of independent structures, solar collectors orbiting the star in a dense cloud, each one catching a fraction of the light. From a distance, it would look like the star had dimmed, not gone dark completely, but faded, because most of its light is being intercepted before it reaches space, and the energy that's captured gets used, which means it eventually gets radiated back out as waste heat. Infrared radiation. Heat signatures that we could detect with the right instruments, even from thousands of light years away. The logic is elegant. If advanced civilizations exist, and if they follow the same physics we do, they need energy. Stars are the best energy source in the universe. A Dyson sphere or swarm is the most efficient way to harvest that energy. Therefore, we should be able to detect them, not by looking for radio signals or optical anomalies, by looking for stars that are dimmer than they should be and hotter in the infrared than makes sense, artificial structures blocking natural starlight and radiating waste heat. The signature should be obvious, so we looked. NASA's Wide Field Infrared Survey Explorer, WISE, spent years scanning the sky in infrared wavelengths. The Kepler Space Telescope, designed to find exoplanets by watching for stars that dim when a planet passes in front of them, also gave us the data to spot unusual dimming patterns that didn't match planets. Astronomers have surveyed hundreds of thousands of stars, specifically looking for Dyson sphere candidates, and the result, after decades of searching, is nothing. No confirmed detections. No stars with the right combination of dimming and infrared excess that would point to a megastructure. A few candidates showed up, strange objects like Tabby's star, a star in the constellation Cygnus that dimmed irregularly and dramatically in ways that didn't fit any known natural explanation. For a while, the internet went wild with speculation. Alien megastructure, Dyson swarm under construction. Finally, evidence. Then astronomers kept watching and collecting data, and the explanation turned out to be dust, a cloud of debris, possibly from a disintegrating comet or a recent collision between planets, passing in front of the star and blocking the light at irregular intervals. Natural. Boring? Not aliens. Every other candidate has gone the same way. Initial excitement, followed by careful observation, followed by a mundane explanation, dust. Variability in the star itself, instrumental error, no megastructures anywhere. That absence is strange. If Dyson spheres are the logical endpoint of energy-hungry civilizations, and if the galaxy is billions of years old, we should see them. Not one or two, thousands. Every civilization that reached a certain level of advancement should have built one, and yet the galaxy looks natural. Stars burning away, radiating their light into the void, unobstructed. No one is harvesting them. Or if they are, they're doing it in a way we can't detect, which brings us back to the uncomfortable question: are we looking for the wrong thing? Freeman Dyson himself acknowledged this problem late in his life. In interviews, he said that the Dyson sphere was just one possibility. It was the solution that made sense to him in 1960, based on the technology and energy needs of mid-20th century humanity. But he admitted that a civilization 1,000 years more advanced might have moved on to something else. Something we can't predict because we don't have the physics yet. Maybe they're harvesting energy from black holes. Penrose processes extracting rotational energy from spinning black holes, a concept that's theoretically possible, but requires engineering at scales we can't even sketch out. Maybe they've figured out how to tap zero-point energy, the quantum fluctuations in empty space that could, in principle, provide limitless power if you knew how to access it. We don't even know if it's possible. But a civilization with a few million years of research might have cracked it. And if they have, they don't need Dyson spheres. They don't need to dismantle planets or block starlight. They're pulling energy out of the vacuum, and we'd never see it because there's no waste heat, no infrared signature, no dimming. Just clean, invisible power. Or maybe the whole premise is wrong. Maybe advanced civilizations don't grow. We assume that technology leads to expansion, that more energy means more industry, means more construction, bigger, louder, more visible. That's how human civilization has worked for the last 10,000 years. But it's a sample size of one. Maybe growth is a phase, a stage that civilizations pass through and then move beyond. Maybe once you've solved the basic problems of survival, once you've got enough energy and resources to keep everyone comfortable, you stop expanding, you stabilize, you turn inward. You focus on art, philosophy, virtual realities, experiences that don't require dismantling solar systems. A post-growth civilization wouldn't build Dyson spheres because they wouldn't need them. They'd be sitting on their home planet, or a small cluster of habitats, living quietly, consuming a fraction of the energy they could theoretically access, because they've decided that's enough. That's a hard idea to swallow if you're steeped in the logic of capitalism and expansion. Infinite growth is baked into our economic systems, our political structures, our vision of the future. But infinite growth is also physically impossible. You can't expand forever in a universe with finite resources. At some point, every civilization hits a ceiling. Maybe the smart ones recognize that and stop before they hit it. Maybe they build sustainable systems that don't require constant expansion. And maybe those civilizations, the quiet ones, the ones that aren't building megastructures or broadcasting their presence, are the ones that survive. The loud ones, the ones that keep growing until they collapse under their own weight, or run out of resources, or attract the attention of something hostile, those are the ones that go extinct. The galaxy selects for sustainability, and sustainability is invisible. Then there's the possibility that Dyson spheres are just a bad idea. Maybe advanced civilizations tried them and decided they weren't worth the effort. Dismantling a planet is an extraordinary engineering project. You're talking about taking apart a body with the mass of Earth or Jupiter, moving quadrillions of tons of material into orbit, assembling it into functional structures while dealing with orbital mechanics, gravitational interactions, and the structural stresses of objects that size. It would take centuries, maybe millennia. And for what? A lot of energy, sure, but also a lot of risk. A Dyson swarm is inherently unstable. Collisions between collectors are inevitable. Maintenance becomes a nightmare. And if something goes wrong, if a significant chunk of the swarm fails or collides or deorbits, you've got debris raining down on your remaining infrastructure. The whole system could cascade into failure. Maybe civilizations run the numbers and decide it's not worth it. Maybe they stick with smaller, more manageable solutions, fusion reactors, orbital solar farms, localized energy production that doesn't require disassembling a solar system. Those solutions wouldn't be detectable from interstellar distances. We'd never see them. And if that's the path most civilizations take, then the absence of Dyson spheres doesn't mean there are no advanced civilizations. It just means they're smarter than we thought they'd be. They're not building monuments, they're building systems that work. The second assumption we need to question is interstellar travel. We've been talking about the Fermi Paradox as if the problem is detection. Where are the signals? Where are the megastructures? Why haven't we seen anyone? But Fermi's original question wasn't about signals, it was about visitors. Where is everybody? Why haven't they come here? And the simplest answer to that question is that interstellar travel is impossible. Not in the sense that the laws of physics forbid it, in the sense that it's so difficult, so resource-intensive, so slow that no civilization bothers. The distances are obscene. The nearest star system to Earth is Alpha Centauri, about 4.3 light-years away. That's 40 trillion kilometers. Voyager 1, the fastest human-made object currently leaving the solar system, is moving at about 17 kilometers per second. At that speed, it would take 70,000 years to reach Alpha Centauri. 70,000 years, longer than human civilization has existed. And that's the closest star. Most stars in the galaxy are thousands or tens of thousands of light years away. Even if you could build a ship that traveled at 10% the speed of light, a speed that would require technology we can't even begin to design, a trip to a star 10,000 light years away would take 100,000 years. One way, no one is making that trip. Not with biological crews. Not unless you've solved immortality or figured out generational ships where the descendants of the people who launched arrive at a destination their great-great-great-grandparents never saw. That's not exploration, that's exile. You could send robots, self-replicating probes, von Neumann machines that arrive at a star system, harvest the resources they need to build copies of themselves, and send those copies to other stars. Exponential expansion. One probe becomes two, two become four, four become eight. Within a few million years, you've seeded the entire galaxy. That's the theory, but no one has seen any evidence of such probes. The Earth hasn't been visited by a self-replicating machine from another star system, at least not in the last few 100 million years, which is the window we could potentially detect through geological or fossil records. The solar system doesn't have artificial objects older than our own satellites. If someone sent von Neumann probes, they either didn't make it here, or they came and left and took their traces with them, or they're so well hidden we wouldn't recognize them if we tripped over one. Maybe interstellar colonization is a dead end. Maybe every civilization that runs the numbers realizes the same thing. The return on investment is terrible. The energy cost of sending even a small probe to another star is astronomical. You're accelerating mass to relativistic speeds, which means you need to overcome the tyranny of the rocket equation, where most of your fuel is spent lifting more fuel. And when the probe arrives, what does it do? It sends back data that takes decades or centuries to reach you. By the time you get the results, the civilization that launched the mission might have collapsed or evolved into something that doesn't care anymore or gone extinct. Why spend the resources? Why not stay home, where the sun is warm and the resources are already accessible and you don't have to gamble on what might be out there in the dark? Carl Sagan used to say that the absence of visitors doesn't mean interstellar travel is impossible. It might just mean it's hard. And when something is hard, you don't do it unless you have a really good reason. Human beings climbed Mount Everest because it was there. We went to the moon because we could, and because it was a political statement during the Cold War. But we stopped going to the moon once the political motivation disappeared. We haven't been back in more than 50 years, not because we can't, because it's expensive and the return doesn't justify the cost. Interstellar travel might be the same, possible in theory, impractical in reality. And the civilizations that recognize that early save themselves the trouble and stay home. The third assumption is the one we almost never question because it's so baked into how we think. We assume that if intelligent life exists, we'll recognize it, that intelligence looks a certain way, acts a certain way, builds certain things. We're looking for radio signals because that's what we use. We're looking for industrial byproducts, atmospheric pollution, heat signatures from cities and factories, because that's what our civilization produces. We're expecting aliens to be like us, tool users, builders, communicators, social species with technology and curiosity and a desire to reach out. But intelligence doesn't have a blueprint. Evolution on Earth has produced one kind of intelligence in humans, and several other kinds in dolphins, elephants, octopuses, crows. None of those species are building radio telescopes. Not because they're not intelligent, because their intelligence evolved to solve different problems in different environments. An octopus is stunningly smart. It can solve puzzles, use tools, change its color and texture to blend into complex backgrounds in milliseconds. But octopuses are solitary. They don't build societies. They don't pass knowledge between generations because they die before their offspring hatch. Their intelligence is wasted, from a technological perspective, because the environmental pressures that shaped them didn't reward cooperation or cumulative culture. Intelligence exists, technology doesn't. Now scale that up to an alien biosphere. Life that evolved in an ocean under an ice shell, like Europa or Enceladus. No line of sight to the stars. No fire, because there's no oxygen atmosphere and everything is underwater. How does a species like that develop astronomy? How do they even conceive of space? They're intelligent, maybe more intelligent than we are, but their entire reality is bounded by ice and water. They might have complex languages, art, philosophy, but they're never building rockets because the concept of leaving their environment doesn't make sense to them. They don't know there's anything to leave. Or take a species that evolved on a planet with a thick atmosphere, permanent cloud cover. They never see the stars. Their night sky is blank. They develop technology, sure, chemistry, medicine, engineering, but they don't develop space travel because they don't know space exists. To them, the universe is their planet, and the idea that there's more beyond the clouds is a fringe theory proposed by a handful of eccentric scientists that no one takes seriously. We'd never detect them. They'd never detect us. Both civilizations intelligent, both technological, both completely unaware of each other because their environments didn't point them in the same direction. And that's assuming carbon-based biology, water as a solvent, DNA as an information storage system, all the things that worked on Earth. But Earth's biology is a sample size of 1. We have no idea if life elsewhere follows the same template. Silicon-based life has been speculated about for decades. It doesn't work well at Earth temperatures, but at higher temperatures, silicon chemistry gets more flexible. Maybe there are organisms on a hot planet orbiting close to a red dwarf that use silicon instead of carbon. They'd look nothing like us. Their biochemistry would be alien in the most literal sense. We wouldn't recognize them as life unless we knew exactly what to look for. Or take it further. Arthur the 100th Clarke, in his novel 2010 Odyssey 2, introduced the idea of life in the atmosphere of Jupiter. Enormous gas bag creatures floating in the upper cloud layers, feeding on organic molecules synthesized by lightning, never touching solid ground because there is no solid ground. They're alive. They might even be intelligent, but they're not building cities or broadcasting signals. They're just existing, doing their thing, completely invisible to us because we weren't looking for floating gas bags. We were looking for planets with solid surfaces and liquid water. Jupiter doesn't qualify, so we write it off as uninhabitable and we move on, never realizing we just flew past a biosphere. The fourth possibility is the one that edges into philosophy and makes scientists uncomfortable: the transcendence hypothesis. The idea that sufficiently advanced civilizations don't stay physical. They don't build Dyson spheres or starships or radio transmitters. They upload. They convert their consciousness into software, into information, into something that doesn't require atoms anymore. And once they've done that, they leave. Not physically. Physically, they might still be sitting on their home planet, a server farm running quietly, maintaining the uploaded minds of trillions of individuals. But experientially, they've moved on. They're living in simulated realities that are richer, more complex, more interesting than anything the physical universe can offer. Why explore the galaxy? when you can create 1,000,000 galaxies inside a computer and explore those instead? Why wait decades for a signal to travel between stars when you can instantiate entire civilizations inside a simulation and interact with them in real time? This idea shows up a lot in science fiction, but it's not just fiction. Physicists and philosophers have taken it seriously. Nick Bostrom, the philosopher at Oxford who's written extensively about existential risks and the nature of reality, has argued that if civilizations can create simulations detailed enough to house conscious beings, and if they create many such simulations, then statistically speaking, we're probably in one. The math is simple. If there's one base reality and 1,000,000,000,000 simulated realities, the odds are 1,000,000,000,000 to 1 that you're in a simulation. You don't know you are because the simulation is detailed enough to be indistinguishable from the real thing. You're a pattern of information running on a substrate you can't directly access, and the universe you observe is a rendered environment designed to look consistent. If that's true, then the Fermi Paradox has a straightforward answer. The universe is silent because most of it is empty. The real action is happening inside simulations created by the few civilizations that reached the technological level needed to build them. Those civilizations aren't exploring space, they're exploring computation space, a realm vastly larger and more malleable than the physical universe. They've transcended, and we're either too early in our development to have done the same, or we're already in one of their simulations and the silence is by design, a controlled environment where the creators don't want us detecting them yet. Maybe we're an experiment, maybe we're entertainment, maybe we're a backup, a preserved snapshot of what their civilization looked like before they transcended. We don't know. We can't know, and if the hypothesis is true, we'll never find anyone out here in the physical universe because there's no one left to find. They're all inside, and the door is closed. The fifth explanation is subtler and maybe more plausible. The Galactic Club exists. Advanced civilizations are out there right now, communicating, trading information, coordinating on projects we can't even imagine. But they're not using radio. They're not using anything we can detect. And even if they were, they're not talking to us because we're not part of the club yet. We haven't met the criteria. We haven't proven we're worth their time. This is different from the zoo hypothesis, where advanced civilizations are deliberately avoiding contact for our benefit. The Galactic Club doesn't care about our benefit. It's not malicious, but it's not benevolent either. It's pragmatic. The club exists to facilitate communication and cooperation among civilizations that have something to offer each other. Knowledge, resources, labor, whatever the currency is at that level. And we, sitting on a single planet, having just barely figured out how to leave our atmosphere, have nothing to offer. We're the equivalent of a Bronze Age village trying to negotiate a trade deal with a modern industrial nation. The nation isn't hostile, it just has no reason to engage. The transaction costs are too high and the potential benefits are too low, so they ignore us. Not out of contempt, out of indifference. Maybe the club communicates on channels we haven't discovered yet. Neutrino beams, which would pass through planets and stars without interacting, undetectable unless you have a massive detector pointed in exactly the right direction at exactly the right time, or quantum entanglement, instantaneous communication across any distance if you've got the technology to set up entangled pairs ahead of time, or gravitational waves, modulated carrier waves in space-time itself. We only just detected gravitational waves in 2015, and that was from colliding black holes, the loudest events in the universe. If someone is sending a modulated signal at a fraction of that amplitude, we'd never notice. We don't have the sensitivity, we don't have the bandwidth. We're listening to the universe with a pair of tin cans and string, and they're using fiber optics. The signal is there. We're just too primitive to decode it. Maybe the club operates on timescales we can't match. Human civilization, the version that builds cities and writes things down, is about 10,000 years old. The industrial phase, the part where we've had machines and electricity and radio, is less than 200 years old. That's a blink. If the Galactic Club has been running for 1,000,000 years, they're not going to notice us yet. They're operating on geological timescales, where a message sent might not get a reply for 10,000 years, because that's how long it takes the recipient to process the information, discuss it with their population, and formulate a response. By the time they get back to us, human civilization might have collapsed or transcended or evolved into something unrecognizable. We're moving too fast, burning too hot. They're waiting to see if we stabilize before they spend the effort on first contact. And then there's the possibility that terrifies me more than any of the others. We're in the club's database. They know we're here. They detected our radio emissions decades ago, logged our location, noted the biosignatures in Earth's atmosphere. They've been watching, and they've decided we're not interesting. Not because we're too primitive, because we're typical. A standard industrial civilization following a predictable trajectory. They've seen 1,000 species like us. Some of them made it, most of them didn't. We're not special. We're not unique. We're just another entry in a long list, and they're waiting to see which category we fall into before they bother making contact. If we survive the next few centuries, if we get through climate change and nuclear brinksmanship and AI and resource depletion, maybe then we get the call. Congratulations, you passed the test. Here's the welcome packet. But if we don't, if we collapse or go extinct, they'll just update our file. Another failed civilization. Archive it and move on. There are plenty more where we came from. That's the most humbling version of the silence, not that we're alone, that we're common, one of millions of species going through the same struggles, the same risks, the same checkpoints. And the ones on the other side of those checkpoints aren't reaching back to help, because help would interfere with the test. You don't get into the club by being rescued, you get in by surviving. And survival is the membership fee. Either you're strong enough, smart enough, lucky enough to make it, or you're not. The universe doesn't grade on a curve. There are no participation trophies. You pass or you fail, and the only way to know which one you are is to keep going and see if you're still here in 1,000 years. All of these possibilities share a common thread. The silence doesn't mean we're alone. It means we're ignorant. We're looking for the universe to behave the way we expect it to, and when it doesn't, we assume there's nothing there. But the universe doesn't owe us clarity. It doesn't owe us signals we can understand, or structures we can recognize, or visitors who show up and introduce themselves. It's under no obligation to make itself comprehensible to a species that's been technologically advanced for less time than it takes a giant sequoia to grow. We're infants. Cosmically speaking, we just opened our eyes. And we're wondering why the adults in the room aren't bending down to our level and explaining everything in terms we can grasp. Maybe they are explaining. Maybe the explanations are all around us, encoded in phenomena we've observed but don't understand. Pulsars, fast radio bursts, the structure of the cosmic web. Maybe those aren't natural. Maybe they're artificial, and we just don't have the reference frame to see the design. Or maybe the adults aren't explaining because they've learnt that explaining doesn't help. You can't teach calculus to someone who hasn't learnt arithmetic. You can't show someone a symphony if they've only ever heard a single note. We're at the single note stage. And the rest of the universe is playing symphonies we don't have the ears to hear yet. That's not their failure, it's ours. And the only way forward is to keep learning, keep building, keep expanding our understanding until the day we finally hear something we recognize, or the day we realize we've been hearing it all along and just didn't know how to listen. There's a question that doesn't get asked often enough in discussions about the Fermi Paradox, and when it does come up, it usually gets brushed aside because the implications are too strange, too humbling, or too terrifying to sit with for very long. The question is simple: what if we're first? Not first to look up at the stars and wonder, first to exist at all. The first species in the entire Milky Way, may be the first in the entire observable universe, to reach the point where we can ask the question, 200 billion stars in this galaxy, 2 trillion galaxies beyond it, billions of years of cosmic history stretching back to a time when Earth didn't exist, when the sun didn't exist, when the atoms in your body were still scattered across interstellar clouds. All that time, all that space, and somehow, against odds that seem impossible, we're the ones who showed up first. It's a ridiculous idea on its face. The universe is 13.8 billion years old. The Milky Way has been forming stars for more than 13 billion years. Our sun is only 4.6 billion years old, which makes it middle-aged by galactic standards, younger than the majority of stars out there. If intelligence is a natural outcome of evolution, if life emerges wherever conditions allow and complexity follows given enough time, then someone should have gotten here before us. Millions of years before us, billions even. The fact that we can't detect anyone suggests that either intelligence is so rare it's only happened once, or the thing that stops civilizations from becoming visible is so effective that no one survives long enough to leave a mark. Those are the standard answers. The great filter behind us or ahead of us. Life is rare or death is common. But there's a third possibility that doesn't require a filter at all. Maybe we're just early. Not impossibly, miraculously early. Just early in the normal statistical sense. Someone has to be first. In any process that unfolds over time, there's always a leading edge. The first star to ignite, the first galaxy to form, the first molecule to replicate. Why couldn't we be the first species to reach technological intelligence? Not because we're special, because the conditions that allow for technological civilizations only became common relatively recently, and we happen to be one of the first to benefit. This is called the early bird hypothesis, and it was formalized by researchers trying to explain the Fermi Paradox without invoking catastrophic filters or cosmic predators. The argument goes like this. For the first few billion years after the Big Bang, the universe was a rough place. Stars were forming, sure, but they were almost entirely hydrogen and helium. The first generation of stars, the ones astronomers call Population 3, contained virtually no heavy elements because heavy elements didn't exist yet. They had to be created inside stars, forged in the nuclear furnaces at their cores, and then scattered into space when those stars went supernova. That process takes time, a lot of time. The first generation of stars lived fast and died young, most of them going supernova within a few million years. Their explosions seeded the surrounding gas clouds with carbon, oxygen, nitrogen, iron, all the elements you need to build rocky planets. The second generation of stars formed from that enriched gas, and when they died, they added even more heavy elements to the mix. By the third or fourth generation, the interstellar medium had enough metals, that's what astronomers call anything heavier than helium, to start forming planets like Earth. But even then, the galaxy wasn't necessarily habitable. The early universe was violent. Star formation rates were much higher, which meant supernova rates were higher too. A young galaxy is constantly being flooded with high-energy radiation from exploding stars, gamma-ray bursts, active galactic nuclei powered by supermassive black holes feeding on infalling gas. Any planet unlucky enough to be near one of those events would be sterilized. The surface blasted by radiation, the atmosphere stripped away. Life might start, but it wouldn't last. The safe zones, the regions where a planet could exist for billions of years without being fried, were rare. It wasn't until the universe was roughly 9 to 10 billion years old, according to models published by researchers studying galactic habitability, that conditions settled down enough for complex life to have a realistic shot at survival. That's when star formation started slowing. That's when the supernova rate dropped. That's when the galaxy became a place where a planet like Earth could form, cool, develop oceans, and sit there undisturbed for the billions of years it takes for single-celled organisms to evolve into something capable of building radio telescopes. 9 billion years after the Big Bang is roughly 4 to 5 billion years ago, which is almost exactly when Earth formed. We didn't arrive early in the history of the universe. We arrived right on time, at the leading edge of the window when technological civilizations could reasonably be expected to start appearing. And if that's true, if the conditions for intelligence only became common in the last few billion years, then the fact that we don't see anyone else isn't strange. It's expected. We're not late to the party, we're early. The party hasn't started yet. This isn't just speculation. In 2015, a team led by astrophysicist T.S.V.I. Piran published a paper arguing that most of the galaxy was uninhabitable until relatively recently. They calculated the rate of gamma-ray bursts and supernovae in different regions of the Milky Way over cosmic time, and concluded that the habitable zone, the region where a planet could survive long enough for life to develop, was much smaller in the early universe than it is now. Planets forming near the galactic center, where star density is high, would have been subjected to lethal radiation events every few 100 million years. Planets forming in the outer regions, where star density is low, wouldn't have had enough heavy elements to build rocky worlds in the first place. Earth sits in what they called the Goldilocks zone of the galaxy, far enough from the center to avoid constant bombardment, close enough that there were sufficient metals in the protoplanetary disk to form a planet. And even in that zone, Earth only became viable in the last few billion years. If Piran's model is correct, and other studies have reached similar conclusions, then Earth is among the first generation of truly habitable planets. Not the only one, but one of the early ones. And if we're early, then the silence makes sense. We're not detecting anyone because there's no one to detect yet. The civilizations that will fill the galaxy are still in their microbial phase, or their early multicellular phase, or they haven't even started yet because their planets are still cooling. We're alone not because we're rare, but because we showed up at the dawn of the era when intelligence becomes possible. We're the morning shift, the first ones through the door. That's the optimistic version of being first. It means the galaxy is ours to explore. No competition, no predators, no ancient civilizations with a billion-year head start who see us as a threat or a resource. Just empty real estate waiting for someone to move in. If we survive the next few centuries, if we get through climate change and nuclear weapons and AI alignment and all the other filters sitting in our immediate future, then we get to be the elder race, the ones who spread across the stars, establish the first interstellar civilization, maybe even seed other planets with life. If we find that life hasn't started there on its own, we'd be the founders. The first chapter in the story of intelligence in the universe. But there's a darker version. Maybe we're not first. Maybe we're last. The last bird hypothesis is newer, stranger, and harder to wrap your head around because it requires thinking about the universe not as it is now, but as it will be trillions of years from now. The argument starts with star formation. Stars don't form at a constant rate. The universe had a peak, a golden age of star formation that happened roughly 11 billion years ago, about 3 billion years after the Big Bang. That was when galaxies were churning out new stars at the highest rate in cosmic history. Gas was abundant. Collisions between galaxies triggered massive bursts of star formation. The universe was bright, hot, crowded with young blue stars burning through their fuel at a ferocious pace. Since then, star formation has been declining. The gas that forms stars is running out. Some of it gets locked up in existing stars. Some of it gets blown out of galaxies by supernova winds and active galactic nuclei. Some of it just falls into the voids between galaxy clusters and drifts out of reach. The rate at which new stars form today is a fraction of what it was 11 billion years ago, and it's still dropping. In another few trillion years, star formation will slow to a trickle. Eventually, it will stop entirely. The universe will run out of the raw materials to make new stars, and the galaxies will go dark as the existing stars age and die. Here's where it gets unsettling. Most of the stars that will ever exist have already been born. The peak of star formation is behind us. The universe is past its prime. And if stars are past their peak, then so are planets, so is life. The majority of habitable planets that will ever exist in the history of the universe formed during that golden age of star formation 11 billion years ago, which means the majority of life, if life is common, should have arisen back then, billions of years before Earth existed. We're not early, we're late, enormously, incomprehensibly late. We're living in the twilight of the universe's ability to produce civilizations, and everyone who came before us is gone. Why are they gone? That's the question the last bird hypothesis doesn't answer cleanly, and that's where it edges from cosmology into existential dread. If the galaxy was full of civilizations billions of years ago, and none of them are detectable now, then something happened to all of them. Maybe they destroyed themselves. Maybe they hit the great filter and didn't make it through. Maybe they transcended, uploaded, left the physical universe behind. Or maybe they just died, naturally, the way species do. They rose, they flourished, they expanded as far as their technology and resources allowed, and then they declined. Resources ran out, suns aged, entropy caught up. They faded into the dark, and the galaxy moved on without them. If that's true, if the universe is a graveyard full of extinct civilizations, then we're not pioneers, we're archaeologists. Standing on a planet that only just became habitable, looking out at a galaxy that used to be crowded and is now empty, trying to piece together what happened. The silence isn't a mystery, it's an echo. The sound of a party that ended billions of years ago, and we're the ones who showed up after everyone went home. That's the last bird scenario. Humanity isn't the beginning of the story, we're the epilogue. The final species to reach intelligence before the universe ages out of the conditions that make intelligence possible. The stars will keep burning for trillions of years, but the new ones, the ones forming now, are smaller, redder, longer-lived, red dwarfs. They'll outlast every other type of star, but they're dim, and their habitable zones are so close to the star that any planet sitting there gets tidally locked. One side always facing the star, baked by radiation and flares, the other side in permanent darkness, frozen solid. Not great for life. Not impossible, but much harder. The galaxy's future is dim, cold and quiet, and if we're one of the last species to arise during the era when habitable planets were still common, then we're inheriting a universe that's already dying. Both possibilities, early bird and last bird, lead to the same uncomfortable conclusion. We're alone. Not because life is rare, but because of timing. Either we're so early that no one else has gotten here yet, or we're so late that everyone else is already gone. In both cases, the galaxy is ours by default, not because we earned it, because we're the only ones left standing, or the only ones standing yet. The distinction matters philosophically, but practically, the result is the same. When we look out at the stars, we're looking at empty real estate, no neighbors, no rivals, no mentors, just us and a whole lot of silence. Carl Sagan used to say there are two possibilities. Either we are alone in the universe or we are not. Both are equally terrifying. The early bird and last bird hypotheses suggest a third option that's somehow worse. We're alone right now, but we might not be forever. Or we're alone now, but we weren't always. Loneliness with an expiration date. Isolation with a history. The idea that the universe is capable of producing intelligence, has produced it, maybe even produced it abundantly, but the timing is such that we're never going to meet anyone. We missed them by 1 billion years, or they'll miss us by 1 billion years, and the gap is unbridgeable. That's not comforting, that's tragic. It also places an enormous weight on humanity's shoulders. If we're early, if the galaxy is empty and waiting for someone to fill it, then what we do in the next few centuries matters in a way that's almost impossible to comprehend. We're not just deciding the fate of 8 billion people, we're deciding whether intelligence has a future in this galaxy. If we destroy ourselves, if we hit one of the filters and don't make it through, then the galaxy stays empty for potentially millions of years until the next species reaches our level. And maybe they make it, or maybe they don't. Maybe intelligence is common enough that someone will eventually get through, but every failure delays that outcome. Every civilization that collapses is a setback for the entire process. And if we're late, if we're the last ones, then the stakes are even higher, because if we fail, that's it. The galaxy doesn't get another chance. The conditions that made Earth possible, the stable sun, the heavy elements, the timing that allowed 4 billion years of uninterrupted evolution, those conditions are fading. The universe is moving into a phase where planets like Earth become rarer. Star formation is slowing. The window is closing, and if we're standing at the edge of that window, if we're the final species to reach technological intelligence before the universe ages out of the ability to produce more, then our survival isn't just about us. It's about whether intelligence has any future at all. We're the last shot, the final roll of the dice, and if we fail, the universe goes dark. Not physically. Stars will keep burning for trillions of years, but consciously, no one left to observe, to understand, to ask questions, just matter drifting through an expanding void, following the laws of physics, signifying nothing. That's a lot of pressure. Too much, maybe. It's the kind of realization that makes you want to close the browser tab and go do something else, anything else, watch a movie, go for a walk. Pretend the universe isn't balanced on the edge of a knife and you're not standing at the fulcrum. But the pressure is there whether we acknowledge it or not. If the early bird hypothesis is correct, we're in a position of cosmic significance, the first technological species in the galaxy, the ones who set the template for what comes after. Do we colonize carefully, preserving the environments we find, or do we strip mine planets and move on? Do we seed life where we find none, or do we leave it alone? Do we build a society that lasts, or do we burn bright and fast and leave ruins for whoever comes next? Those decisions matter, not just to us, to everyone. And if the last bird hypothesis is correct, we're in a position of even greater significance. The final representatives of intelligence in this corner of the universe, the ones who get to decide whether the story ends with us or continues. If we survive, if we spread, if we find a way to outlast the dying of the stars, then intelligence persists, consciousness persists. The universe gets to keep knowing itself. But if we fail, if we collapse or go extinct, then that's the end, not of matter, not of energy, but of meaning. The universe continues, but there's no one left to care. It's worth pausing here to acknowledge that both hypotheses might be wrong. We might not be first or last. We might be somewhere in the middle of a long continuum of civilizations that rise and fall on timescales we can't detect. The galaxy might be full of intelligence, just not the kind we're looking for or not using communication methods we recognize. The Fermi Paradox might have a simpler answer that we haven't thought of yet. We don't know. We have data, we have models, but the sample size is one. Earth, us, everything else is extrapolation. But the early bird and last bird scenarios are worth taking seriously because they're both consistent with the data we have. The universe is 13.8 billion years old. Star formation peaked 11 billion years ago. The galaxy is quieter now than it was. We can't detect any other civilizations. Those are facts. And the hypotheses built on those facts, that we're either early or late, fit the silence better than most other explanations. They don't require filters or predators or transcendence. They just require time, lots of it, and a recognition that the universe doesn't operate on human scales. What seems like a contradiction to us, that the galaxy is old but appears empty, might just be a timing issue. We're looking at a snapshot of a process that unfolds over tens of billions of years, and we're trying to draw conclusions from that single frame. It's like looking at a photograph of an empty stadium and concluding that no one ever goes to games. Maybe you just took the picture at the wrong time. The question is, what do we do with that uncertainty? If we don't know whether we're first, last, or something in between, how does that change our behavior? Does it change our behavior? It should, because in every version of the story, survival is the prerequisite. If we're early, we need to survive long enough to become the elder race. If we're late, we need to survive long enough to prove that intelligence can persist even in a cooling universe. If we're in the middle, we need to survive long enough to eventually make contact with whoever else is out there. The common thread is survival. Not just survival in the sense of not going extinct, survival in the sense of thriving. Building a civilization that's stable, sustainable, capable of weathering the crises that topple most species: climate change, resource depletion, war, AI. The filters are real. We're staring at them right now. And the difference between a civilization that makes it and one that doesn't is whether they take those threats seriously and act on them before it's too late. That's why we keep looking. That's why SETI is still listening. Why astronomers are still cataloging exoplanets. Why missions like the James Webb Space Telescope are still scanning the sky for biosignatures and technosignatures. Not because we're confident we'll find something, because the search itself is important. Every star system we rule out narrows the possibilities. Every planet we study tells us more about how common or rare Earth-like conditions are. Every year we don't detect a signal gives us more data about what the universe actually looks like, as opposed to what we hoped it would look like. The silence is informative. It's not the answer we wanted, but it's an answer. And the longer the silence lasts, the more it tells us about where we sit in the cosmic timeline. If we ever do find something, if a telescope picks up an unambiguous signal or a probe detects a biosignature in the atmosphere of an exoplanet, or a lander on Europa scoops up a microbe, the impact will be immediate and profound. Not just scientifically, culturally, philosophically, religiously. Every framework humanity has built to understand its place in the universe will have to be revised. We're not alone. We're not special. We're one instance of a phenomenon that happens elsewhere, that changes everything. The questions we've been asking for centuries: are we unique? Are we important? Why are we here? All of those questions get reframed. We're not the center of the story. We're a chapter. Maybe an interesting chapter, maybe not, but just one piece of a much larger narrative. And if we don't find anything, if we search for another century or 2 or 10, and the silence holds, that's informative too. It means life is rarer than we thought, or intelligence is rarer, or technological civilizations don't last, or we're early, or we're late, or we're looking in the wrong places. The absence of evidence isn't proof of absence, but it's a constraint. It narrows the possibilities, and every year we don't find anyone pushes the probability distribution toward the scenarios where we're more alone, more isolated, more significant than we assumed. Both outcomes are terrifying in their own way. Finding life means we're not special, which is humbling. Not finding life means we might be the only ones, which is overwhelming. Either way, we're forced to confront the reality that the universe doesn't care about us. It didn't design itself for our benefit. It's not waiting for us to succeed or fail. It just is. A vast, ancient, indifferent structure governed by physics, running on timescales that dwarf human history. We're a blip. A brief flicker of complexity in a cosmos that will outlast us by trillions of years. And the only meaning we have is the meaning we create. The only significance we have is the significance we assign ourselves. That's the lens through which we have to view the early bird and last bird hypotheses. They're not predictions, they're frameworks. Ways of understanding the silence that place humanity in a larger temporal context. If we're first, we're the beginning. If we're last, we're the end. If we're neither, we're somewhere in the middle, part of a continuum we haven't mapped yet. All three possibilities are humbling. All three suggest that the universe is bigger, older, and stranger than we give it credit for. And all three place a responsibility on us that we didn't ask for but can't avoid. We're here, we're conscious, we can ask questions, build tools, explore, understand. No other species on Earth can do that. No other species we know of anywhere can do that. And if we're the only ones, even temporarily, then what we do matters, not because the universe is watching, because we're the ones doing the watching. We're the ones who get to decide whether the story continues or ends here. The search goes on. CT keeps listening, telescopes keep scanning, rovers keep drilling into Martian soil, probes keep flying toward the outer solar system, not because we're sure we'll find something, because the act of looking is what defines us. Curiosity, the refusal to accept ignorance when knowledge is possible. The belief, maybe irrational but deeply human, that the universe is comprehensible and that we're capable of comprehending it. That's what drives the search. Not arrogance, hope. The hope that we're not alone. The hope that if we are alone, it's temporary. The hope that the silence will break, and when it does, we'll be ready. And if the silence never breaks, if we search for 1,000 years and find nothing, we'll have learned something. We'll have learned that the universe, for all its scale and grandeur, is a lonelier place than we imagined. That intelligence is fragile, rare, maybe even unique. That we're standing on a small rock in an ocean of darkness, and the light we carry is the only light there is. That's not a comforting realization, but it's not a hopeless one either, because if we're the only light, then keeping it burning matters more than anything. Not for the universe, for us, for the idea that consciousness, brief and improbable as it is, has value. That the questions are worth asking even if no one else is around to ask them. That the search is worth continuing even if the answer is silence. Because we're here, and as long as we're here, the story isn't over. It's just beginning, or ending, or somewhere in between, and the only way to find out which is to keep going and see what happens next. So where does that leave us? Standing on a planet that took 4.5 billion years to become habitable, looking out at a galaxy that's been forming stars for 13 billion and hearing nothing. 200 billion suns in the Milky Way, 40 sextillion planets where water could pool on the surface, trillions of years for anyone to light a fire and call out into the dark. And the only voice we hear is our own, echoing back from the void. We've walked through 30 explanations for that silence. Some of them suggest we're alone because life never started anywhere else. Some suggest we're alone because intelligence is a fluke that almost never happens. Some suggest everyone else is dead, killed by filters we haven't hit yet or dangers we haven't imagined. Some suggest they're hiding, terrified of predators we can't see. Some suggest they're out there right now, talking on channels we don't have the equipment to hear, living in ways we wouldn't recognize as life even if we were staring directly at it. And some suggest we're just early, the first ones through the door in a universe that's only now becoming capable of producing minds like ours. Every explanation is uncomfortable. Every one of them reframes what it means to be human in a way that's either humbling or terrifying or both. If we're alone, that's crushing. If we're not alone but no one survived, that's a warning. If we're not alone but everyone is hiding, that's a threat. If we're not alone but too primitive to notice, that's humiliating. There is no version of this story that lets us walk away feeling safe or special or certain about what comes next. But here's what we know for sure. We're here, we're asking the question, we built the tools to search for an answer, and we're still searching. That might not mean we're special, but it means we're part of something, a process, a pattern, a universe that, for reasons we don't fully understand, became capable of looking at itself. And whether we're the first to do that or the last or somewhere in between, the fact that it's happening at all is extraordinary. The silence isn't empty, it's full of possibility. And the only way to find out what that possibility holds is to survive long enough to keep listening.